hopefully you heard on that video as well, just the acoustically complex environment, and that you had a lot of action going on. And so Sarah also will talk a little bit today about auditing some of the audio files as well. So we'll look through that later on today. Let's go back to the screen share. And I'll just introduce a little bit of today before we get going and get back into the PRH files. So yesterday we were working on finishing up the PRH file. We didn't quite finish all of these aspects, but we will get to these, actually getting these pseudo tracks. We'll get some pseudo tracks and put them into KML files today. We'll estimate swim speed and we'll calculate track plot today. We'll try to do all that in the first part of the day today. And then towards the end of the day, we'll get into some of the stitching video and audio together to actually like make these integrated video files. And that's kind of like, obviously that's the last step. So we're kind of like, I'd love for someone eventually to come to me with like, okay, I made my own PRH file. How do I make these video files? This video file process, just to warn you, it's dependent on things like your screen size and how big your resolution is of your screen size. So there's a lot of opportunities for like different variations here of what's going to work for you. But we can talk about all those for your specific cases as things pop up. So today we will have, so we'll start with some of that information and data. We're switching around. We'll do the videos at the end of the day, and we'll do the kind of the rest of the PRH file this morning. And then we'll get into some awesome guest speakers talking about how to use some of that PRH file once we create it, how to use some of that data. So we'll start us off talking about some event detection with PRHs, and then we'll get Sherelle in there, who has worked a lot on this data and taught a lot of courses through the California Ocean Alliance and through the Salinas High School program that we're raising money for on this workshop. We'll give you guys an update on that tomorrow. And then we'll have Stacy DeReuter come in talking about the awesome tag tools, animal tool stuff that a lot of this workshop depends on, to be honest. So Stacy's gonna come in and talk about some of those tools. And then we'll have Sarah, and I keep meaning to change it. Sarah, Nicole, and Emily will talk about the video audits in Boris. And then we'll have Jen Tackaberry come in and talk about some track plot ideas. So that's kind of the basic outline for today. Just to kind of think about tomorrow, one of the things that we'll talk about tomorrow is people have been asking a lot about how do I adapt these tools into my own tags and into my own ideas, whether it's catch tags or whether it's something completely different. And so, one of the things we did in the rewrite to make this data really work for a variety of things is tried to make really clear that you have these major workhorse scripts going on here, right? Like this, in this cell, in cell 4 here, all of this other stuff is kind of set up to get us to this critical part of this function, the sync bids and data. Here's the inputs you're putting into that function. Here's the outputs. But if you don't have data at all, you're just going to have this switch that says, oh, I just need to initialize these same variables that are coming out of here, but with just to be basically blank, there. And so working behind the scenes, for I would say this week, but really like as far as I can remember, has been this guy, James, who put on the tag I was just showing you guys earlier. James Fallbush will be talking tomorrow. He's been working behind the scenes to really kind of like test a lot of these scripts with other tag types. And he's going to talk a little bit about how to use other tag types and work with long data sets in general. So that's if you're interested in working with other tags, that's a good one. We'll also have a couple of guest speakers towards the latter part of the day. Taylor Chappell's going to come in and talk to us about putting tags on big fish. There's just some other, so we've been talking a lot about whales and I'm getting feedback. So maybe some really big fish there that he's going to come in and talk a little bit about how to do some of those things. And then John Kalamakidis will come in and talk about just some of the ethics of putting on tags and some of the history of tags. Am I completely frozen here? Uh-oh.
And he's back. You are muted right now.
I broke the internet. All good. That video was so awesome. Let's try it one more time because I think you guys got stuck probably right when I was showing the video of what Taylor's doing tomorrow. Let's go back to this, share screen. Sorry for that interruption. So Taylor, Taylor Chappell's going to come in from Oregon State and talk a little bit about putting tags on other kinds of animals like big fish. So this is a really big fish Taylor putting a tag out on, and he'll talk about some of these kinds of tags and working with sharks and doing different kinds of attachment modalities for cats tags and for other tags. And then we'll have John Calamakitis come in and talk to us about some of his history. John Calamakitis has been putting tags on just about as long as anyone, and talk about some of like how do you make decisions about what kinds of tags to use and why on cetaceans and on hopefully some other animals as well. So that'll be our takeaway tomorrow, and we'll also kind of wrap up any loose ends and things like that. So that's kind of what's upcoming. So with that, we're going to go back to working on our PRH file, working on our data. I saw a lot of good success from people working on these yesterday. And we will get back to that today. So I did, get back to some MATLAB. So if you remember yesterday, we're just kind of finishing up this flow noise script, and so we'll basically restart from this point today. I wanted to highlight again, I know a lot of people had issues running the movie time scripts. Specifically, there was an introduced error and they were getting funny graphs at the end. I did push an update up to the make movie time script, which should fix that, so that you now should get a nice figure that when you run the movie time script, you should just get this one without errors. Your lines might be different colors depending on your MATLAB version, but you should get this nice script with no weird gaps in the file. So it was one of those things where it was an old solution to an old problem causing a new problem to a new solution. And so we've updated that piece. Now, one thing you'll notice, for those of you guys who are running this a second time, remember how we had that whole part in there where we had to update our audio files. So we did the WAV files using the FFmpeg, and we put those in a separate folder. Well, if you've already done that step and you have that nice read audio, that audio data folder now in your workflow, you don't need to run that audio step again, that audio processing step, because you already have all of these files. So if you do try to rerun this step, which don't do it necessarily now because this is the one that runs for a long time, but if you do try to rerun that, you can set this flag to false, and that might both reduce your processing time and reduce the chance for errors as it tries to redo something that it doesn't exist anymore, those WAV files that you created. So you might set that flag, just literally change true to false to run that flag. So just have that in your head for today. So I ran that overnight. I ran it on 2020 and 2019. So it should be good to go on those ideas. But let me know if you still have problems. I've already heard some problems, and maybe there's some memory issues that people are having, and so I'll be curious if other people are having that as well. Okay, so we're picking up from where we left off yesterday. If you still have your MATLAB open from yesterday, you can just start straight from there. We're at a point now where people have slightly different answers. Like you did your own tag slips and you did your own whale orientations. So you might have a slightly different now info file and truncate file than we do. So if you want to start over with this, you can just start with these ones from the workshop file, but you could also just use the ones that you've been creating, and that should work. That'll be totally fine. You'll have that information. But I'm going to go ahead and start from scratch again using our workshop files, our kind of basic templates here. And I'm going to just navigate to my folder. So it tells me to select my same things. I'm starting at cell 2 again to start from those pieces. So I'm in my test folder. Select that mat file, and then I'm going to select that header file for those pieces. So then that just loads in just is telling me where to look for all the files that I'm looking for. And now it tells me, okay, I've created through step 10. So I'm going to go all the way down to step 10. And actually I did finish step 10. Yours might say you finished through step 9 if you do this, because I ran this separately. But so we're on step 10. So whether you ran the flow nodes or not, you can rerun this file and it'll kind of load in all the variables that you need. And it'll ask you, okay, so you already ran the flow nodes variable, it already exists. Do you want to rewrite it? I'm just going to say, no, I don't want to rewrite my file here. And so then it'll spit out this graph of your flow noise and your depth profile. And you should have this thing that kind of looks like flow noise. Remember where you have essentially the noise of the hydrophone is a proxy for how fast the animal's moving. And so when you have things like a big dive here, you have that flow noise increasing really rapidly. When you have these feeding events, you have that flow noise increasing really rapidly. And that, of course, will look different for your animal, but you should have these periods of high noise and low noise as that animal's moving faster and slower. Okay, some of you guys, if you didn't update in the last 2 hours, you might have, and you tried to rerun this cell, you might have gotten an error here just about trying to save the audio file there because it's not loaded in there. You can either fix that by just adding in this flag in here, either download it in the GitHub again, or if s equals 1, only run this if s equals 1, or you can just skip it for now. Everything's loaded. You don't have to worry about that error that just popped up and it's asking you to save the audio file. Just check that you got that plot lined up there. That looks good. So far, so good. Nothing's coming in the chat. No one needs to pause. We're ready for a jiggle action. Just to kind of preview that as people are getting kind of caught up here, running cell 2 and cell 10A. Just to say kind of what the jiggle file is doing. Essentially, this is a process. This is one of the reasons we sample the accelerometer so high, because you can get a lot of information from that. We always sample the accelerometer at 400 hertz, or even if you sample it at 50 hertz or higher, you can do some nice things with it. But we always sample pretty high. We don't push it, like cats can go up to 800 hertz, I think. We try not to push it to the limits of that because there's just more chance to introduce errors. So we tend to do like 400 hertz as a compromise, and that gets us the information we need. And some of that information is this. So one of the things, this process comes from this idea that Jeremy Goldbogen was looking at these high frequency sample rate accelerometers and D-tags. And notice things like when the whale is descending, you get these large kind of noisy areas in the accelerometer signal in all 3 axes. And then when the whale is doing things that we expect to be lunges, you get this noisy signal in the accelerometer. And it turns out if you take the amplitude of that noise and correlate that to orientation corrected depth rate, which is basically a way that we can measure speed in situ by looking at how quickly that whale or that animal is ascending or descending. And if it's ascending fairly vertically, you can actually calculate how fast it's going. That's a direct measurement of distance over time. So we can do a correlation between the noise in that speed profile and the orientation corrected depth rate, and actually then have that metric of speed that then we can apply to the whole data set. And say like, okay, well now that we know that correlation, we can apply that correlation to the whole data set. So that's essentially how we measure speed with both tag accelerometer jiggle and flow noise. If you're used to looking at spectrograms, you can kind of see that information here where and you can kind of see the frequency where you have the maximum accelerometer amplitudes that correlate to speed. So that's kind of in that frequency range of like 10 to 50 hertz, you have that accelerometer range. And so that's why you want to sample the accelerometer at least 100 hertz if you can, to be able to capture that frequency noise. If you're too low, you don't really see that high frequency jiggle there. The other thing that just kind of results from that, one reason we'll talk about tomorrow, how to set up your tags. One of the other reasons to calculate high sample rate accelerometer data is that you never really know what you're going to get. You can actually pick up calling behavior on the accelerometer. And there's some nice work from Jeremy Goldbogen and Alison Stimpert and Will Astrick and James Fallbush looking at how the accelerometer can also pick up calling behavior from the animals as well. So this is actually that humpback whale we were just looking at, and you can see that some of that calling behavior actually being picked up at the jiggle accelerometer. Cool. All right, so let's get back to the scripts, the part everyone's waiting for. Okay, so for 10B, basically what it's doing, if you run 10B, just gonna click on run section here. If I run section 10B, you're going to get it's basically calculating that tag jiggle. It's using this subscript to calculate the tag jiggle. And it's just giving you this comparison here between the flow noise, if you have flow noise, and the jiggle. And what you should look for is that you have a kind of a correlation there. It's not going to be perfect, but you're going to have a nice relationship where when one is increasing, the other is increasing as well, because they're essentially measuring the same thing. It's basically noise in the environment. The other reason to kind of check out this graph, and this is a problem with this version of the tag that we're using as the example file, but it should not be a problem moving forward in newer versions of CATS tags and stuff. But if you have old data, this might be a problem to look for, is that you should actually have these be fairly well aligned in time, which would be a signal that your tag camera data and your accelerometer data are well aligned. You can actually see here that there's a little bit of an offset in this data set, that this flow noise data, which comes from the video files, is a little bit offset from this peak in that accelerometer data file. So someone actually asked me about that problem, like they're having a second or two offset between the data and the video in their data files. So there was a version of Cats tags that did have, like in the early 30s, that did have some issues with that. And so if that is a problem for you, we can show you some ways that we correlate it, but often it's basically doing that, lining up that accelerometer and video data. I do have a script right here that is what we used to then realign those using that flow noise and the jiggle accelerometer. We don't have that as like part of the normal outflow, because in the new tags, that should not be a problem. If you're putting out data in the newer versions of the UI, that shouldn't be a problem as far as that we've tested and seen. And we get happy to talk to you guys about some specific ways to test that if you're worried about that in your data. But there was a moment where there was data that was a little bit offset. Not tag numbers, tag UI versions, as Will's saying. The tag UI versions in the early 30s. I think we're at 30. I think the Cats is like at 37 or 38 now. And those newer Cats UIs are all, those firmware versions are up to date. Okay. So we're great. So we got jiggle. We have our section 10B finished. Remember, every time we're looking for this flag that section actually finished completely. I'll try to put in some error checking here. I think some problems people are having are coming up because the sections were having an error and people were moving forward. So I'll put in some tries to make sure that people know to make sure that a section finished and complete that before moving on.
Hey, Dave.
But yeah.
We have a question in the chat. How does the flow noise calculation extract flow noise and not other noise from the audio?
Yeah, great question. So going back to the flow noise question. So there's a couple of, this first parts here of the script is just a setup, like, okay, let's just get our data back from that raw data file from that. So we're just basically redoing the calibrations we did earlier, but just applying the calibrations that we did. So that's how that's setting it up now, and allows us to kind of start at any given cell, saving our past work. And then the flow noise script here, this get flow noise, what it basically does is it looks at the frequency band. And if you dig into that get flow noise script, you can reset that frequency band if you have a specific frequency band you're of interest. I think we do between, I have to remember, it's between 10 and 50 hertz or 10 and 90 hertz or something along those lines to look for that flow noise frequency band. And so there's some defaults set in there automatically that you can get in there and change if you like. But it's not a perfect measurement. Actually, one of the things that this plot is highlighting is that when you have things like noise from a call, you still get that kind of, that it looks the same as a spike in the flow noise, as a spike in speed. So there are issues with doing that. So if you have a noisy environment, you do that. There are some really cool papers out by Paul Weinstein and others that have, and I think Ben de Beckman have, when you have two dual hydrophones in a tag, which we do not have in Cats tags, but D tags have two dual hydrophones, and you can do some cool work separating out the correlation of if the two hydrophones are correlated, it's probably not flow noise. It's probably some other kind of noise that's coming into the tag that's a direct signal. If the two hydrophones are uncorrelated, it is flow noise. And so by separating out the correlation, you can actually separate out flow noise from other noise. So we do not have the sophistication to do that because we only have one hydrophone in the Cats tags. So you do sometimes get these artifacts that you have to be aware of. And this is an indicator sometimes that whales are actually calling. If you're looking at your speed metric and you have these like really weird spikes, and while the whale doesn't seem to be doing anything, that could be an indication to check out your audio file to look for calling behavior in those locations. Sometimes we identify baleen whale calls using that. Does that answer that question? Anything else, Will?
That's the only thing in there.
Sweet. Okay. Let's get at it. Let's do that correlation. Let's measure speed. So we ran our flow noise, we have our jig. So now we have a couple of variables in here. We have flow noise and jig. Jig is set up right now as a 4-column matrix. These are the jiggle axis in all 3 different accelerometer axes, and then the overall amplitude. And so what this script does, and you could run, to be honest, you can run the jiggle amplitude, this script on any of these axes and get a pretty good result. This is set up to be a little bit more robust and even like look at all 3 axes and see which of the 3 axes is the most dominant signal and what contributions of each axis, because that can change depending on the orientation of your tag on the whale, on the animal. Maybe there's direct direct motion coming in right on the X accelerometer, or maybe the tag's rotated and it's coming in on the Y accelerometer. So that can rotate depending on your tag position and orientation. So we use all three axes to kind of correlate that, but nothing you have to worry about. That's just what's happening. So basically same thing, we're gonna set up our data here, and then we're gonna run our workhorse script here, which is this speed from RMS version 3. So we're gonna run that version here, and it's gonna create this first figure here. And this first figure here is a chance to kind of start to threshold our data. In our settings here, you have some basic thresholds you can set, and that's going to be kind of deployment specific. If your animal dives really deeply, like our example animal here, and it's going almost very steeply, you're going to be able to set a higher threshold. The higher the threshold of pitch you use, the more accurate, the more steeply that animal is ascending and descending, and the more accurate your measurement, your correlative measurement of orientation corrected depth rate will be. So the higher you can set this, the better. Not all animals do have really high steep descent and ascents. And so you might have to like sacrifice a little bit of accuracy in order to be able to get this at all. So you might have to lower that pitch value even further if you need to. So ours though, what we're looking for is to get a nice tight correlation between that measured speed, orientation corrected depth rate, and our amplitude here. So you can see a lot of noise in here, and this color schemes are designed to like help you differentiate where that noise is coming from. So in this case, you can see on the color bar here that a lot of the blue dots are really the noise and the orange dots are really the nice accurate spot. So if I can change my threshold here, I can make my correlation even tighter. So by clicking right on this axis, this color bar at around 60, I'll cut off all of those spots that are blue. And I can even make that even a little higher. I have enough data here that I can really have a nice correlative spike there that sets that in there. You know, and you only wouldn't want to do that if you don't really have spots that are above 60 degrees. So you can set that in there. Another piece that's in here, you can also set the roll rate. If your animal's rolling around a lot, that can cause problems because you can still get jiggle from a fast roll, a fast maneuver there. We don't see that necessarily correlated too much. You could set this at 12 or something to kind of get rid of a few of those blue dots, but it's not that big of a deal. But the other big one in here that can be helpful is this depth threshold. So sometimes if the whale's at the surface or in this case at really deep water, you start to get some funny behavior as well. So I can get rid of a lot of these yellow dots here by limiting my depth threshold to only be in a certain region here of where I'm trying to come up with my correlation. Now, just to be clear, we're going to calculate speed for the whole deployment, but this is for the calibration period. I only want to limit it to where it's highly accurate. So we're going to calculate speed for the whole deployment, but this is how we're calculating the regression relationship. So I'm going to, in this case, there's the instructions on the bottom there. On the depth, if I want to cut off higher values, the deeper values, I right click on this color bar. So I'm going to click at about 250 here, right click on that. And that's going to even make my correlation even tighter. So really get rid of some of those noisy values. So there's still some in there, but it's a regression relationship. It'll be fine. We'll cut that off. So, okay, that's good. I'm happy with that. Hopefully everyone's happy with that. I'm going to click enter here and move on to the next section. Next section. Okay, so now we're making apply. This is now our whole deployment here. Now, I'll show you a couple of things here. One is that, so I identified the tag slips on this plot of this depth up here. I identified the tag slips, partially because if your tag slips orientation drastically in your deployment, so if some people are having function finds, keep a list of those. Quat divide looks like one of them. I will, those come from the aerospace toolbox. So if you try to download that aerospace toolbox, that might fix your problem. Also, I'll just try to make a list of any other errors people have, and I will look for those functions individually and try to add them into the CATS tools folder. So we've been basically able to avoid those, but try that aerospace toolbox first if you can get that. Okay, so quat divide is a quaternion. We're using quaternion reference frames again here as we calculate things like tag slips. So tag slips are dangerous when you're calculating speed because you might get a different orientation for your tag depending on, you might get a different calibration depending on how your tag is oriented. If your tag is up at the head of the whale, getting like a really just spot on all of the friction on that tag, you're gonna get a much higher amplitude signal than if the tag is kind of sit there like where a calf might bow ride, right out behind the dorsal fin or something. So if your tag is moving around a lot, might have to have a different calibration period. For this one, that tag didn't really move that much. So it kind of automatically started by saying like, okay, there's really only one speed period for the most part. The tag didn't really move that much. We can kind of like calibrate everything as once. So that's kind of our first sense here. And we can see we have a pretty good correlation here, a 0.93 correlation between our noise and our amplitude of the signal. but I think we can do better actually. So you notice here at the end, so this has some implementations here. I know in some versions you might have this weird overlap between the instructions here in the graph. I'm sorry about that. We'll try to see if we can move that graph over to make that a little bit easier to read. But what you can do is you can zoom in here to kind of check out these correlation signals a little bit better. So this is the speed here. This is the blue line is the speed from the jiggle. The pink line, the magenta line is the speed from the flow noise. And these green and red lines are the orientation corrected depth rate calculated from those thresholds. The red lines are the kind of the initial restrictions the red dots are the initial restrictions that you put in. The green dots are the updated restrictions that we just updated with that graph. So I'm going to left click here and you can kind of zoom in and see that correlation. Actually, I'm going to zoom out to a different spot that's a little tighter, not on this descent here. So you can see that because there's less noise when the animal's not fluking, it's just descending. And you can see that our OCDR in general lines up pretty well with our jiggle amplitude and our flow noise amplitude. That's pretty good. We have flow noise on the right on the bottom graph and jiggle on the left. So right click to zoom back out. Yeah.
There's a question back on the thresholding part. Once we're done with this, maybe we can go back to that for a second.
Cool. Yeah. Well, I will show you how to do that even within this script. So then over here though, you can see that there starts to be some variation here. So I'm going to left click over here, and you can start to see that, particularly in the flow noise, and we'll recalibrate flow noise after this actually to kind of have its own signal. But even in the jiggle, you can start to see some offset between the jiggle and our OCDR values here. So I'm going to right click here and spit out, and I'm actually going to throw in here a tag slip location. I'm going to throw in here a tag slip location. I'm going to press S. The instructions over there on the right. I'm going to add in a new speed period. And basically what that's doing is creating a second plot here. So the first one, there's two plots now, 301 and 302, and they're calculating speed independently of those two areas. And depending on how your tag slipped, you might have started with two periods or not. But you can kind of see now the blue dots here are the regression just for this period versus the green dots are the regression on all. And in this period, like it's still pretty similar. Like this is still a pretty good correlation here between our jiggle and our flow noise. So that now it's even tighter, right? Like those dots are going right over the top of my jiggle speeds. That's pretty great. And then, so I'm going to press enter on this one and go to section 2. I'm going to accept those values and go to section 2. And you can see that in section 2, it's actually way better now. You have a really tight correlation both between the jiggle and the flow noise and the OCDR in this section as well, by kind of limiting that to the calibration to just be in this section. So I'm pretty happy with these. So I'm basically just going to press enter to move on with this. But before I do that, let me check out what question there was. Let's see here. Chat. We've got a bunch of questions coming in. Okay, well, if we're getting errors in the changing the thresholds, so that we'll have to kind of troubleshoot that individually. It's probably related to your specific tag slip locations, but you might just try to restart that and see if how it works. Hopefully other people are able to catch up on this spot. Is everyone else able to move past the threshold section? If other people are getting the same error that Mark is getting and not able to move past, that would be good information, and we'll try to look at that. Mark, hopefully it should work out. So we might have to troubleshoot that individually later on. Okay, so this is it. I'm going to accept these calibration values. And so basically it's moving on. And it's going to ask me here now in the main screen, it's accepting those calibrations. It's going to save these figures. We don't save a lot of the figures that are created for this, but in this situation, we are saving these speed plots. And we do that because as you're making your deployments later on, you might want to know, like, okay, well, how was my speed calibration for this file? Can I actually trust the speed for like highly accurate things or not? And so you save these speed plots as just kind of a reminder if you're ever looking at this deployment later about how accurate my speed deployments were and for which sections they were accurate, so you can know whether or not it's a good deployment to trust or not to trust the speed. The other thing I should point out and emphasize is that you notice that there's a speed floor here. None of these values really get below 1. And that's a product of this regression relationship where you can't really detect, you need some motion, forward motion, in order to be able to detect that noise and that jiggle amplitude or that flow noise amplitude. So you need some noise there. So this method really only works for animals that are moving above 1 meter per second. So if you have a slow moving animal, this method unfortunately probably won't do you very much good. You might see some variation, but you won't see much if that animal is moving slowly. It really only works for faster moving animals. So we'll have to come up with some other metric. That's where there is a need for those like speed sensors that'll have a better, slower moving detector that CATS tags do not have usually. Okay, so that covered that. So what it's asking you for here now is if you want to recalibrate the speed using just for the flow noise. We did that. That was primarily to do the jiggle. That was focused on the jiggle. All the thresholding was at the jiggle, but the flow noise, and in this case, the flow noise was done at the same time. It actually looked pretty good. Like we had a pretty good correlation with flow noise and jiggle here too. Just for the sake of argument, we'll just go ahead and say like, yeah, let's just make a separate calibration just for the flow noise as well. So I'm just going to type in 1 on my main screen here. And that'll just give me another chance to look at just the flow noise data and look at the thresholding in the same way for the flow noise data. You can see it's a little bit noisier than the jiggle in this case. It won't always be that way, but similar kinds of things here. I can readjust my thresholds, get rid of a lot of those kind of lower valued spots. And then similar thing here, I can get rid of a lot of that really deep water stuff and make a nicer correlation here. And so this will help me make a really nice flow noise calibration here. So I'll press enter. Similar kind of thing. I got a pretty good 0.78 correlation, but you can see it really rapidly deteriorate here towards the end. So I'm going to add, so these are all pretty good. So I'm going to add in a separate speed section here, pressing S. So it's going to make these 2 separate sections. And now we can see actually really nice correlation. So in the first section, we have a 0.89 correlation. And in the second section, we have a 0.9 correlation. So you don't have a lot of points here, but even with just these few points, you're making a really nice correlation between the OCDR and the speed sensor. So that's kind of that for speed. I'll press enter here again to accept those calibrations, and we'll move on in this section. Yeah.
Really quick, could we just go through on that graph on the bottom there on that regression graph, just kind of like what's going on there. In terms of like the little dotted lines and things like that?
Yeah, great question. So we have 2 sections, remember, of data here. So the blue dots are just the data just from this section, and the green dots include data from all of the other sections. So the green data green dots are data from section 2 essentially here. And so then the green line is kind of a reminder that, okay, if I regress on all equations, I have that 0.78 correlation. And it would kind of look like this equation. If I limit it just to this section, I have this 0.89 correlation on the pink line just through those blue dots. And that's an indication that like, oh, okay, that's actually pretty good. That's better to have these different sections. And the same thing here, like if the green dots here or include all of the data, and you can see that this section's data is kind of offset. And so that's why it's better to have these 2 different sections, because this section's data is kind of different than that other section data because the tag slipped in its orientation. The dashed lines here are the prediction interval. So you can calculate confidence intervals and prediction intervals of your regression. And it's the 68% prediction interval. It's just like one metric of what your error is. And all of the other prediction intervals, the speed prediction intervals and the confidence intervals and stuff, all of that is spit out in this speed table here. So your speed table is kind of your variable that's going to have all those different information. So if you ever want to then plot speed or something, you can plot speed.jj. That's your speed from your jiggle. You can spot speed.fm. That's your speed from your flow noise. Speed.sp is the sign of the pitch. That's your OCDR. So you could calculate that as well for the threshold of the areas that you did when you said, okay, it's only pitches higher than 60 degrees. So you have that whole line there that gives you speed for your whole deployment, and it's the same length and same size as all of my other variables, as my depth and my pitch and my roll. So I have speed for all of those. These values then are the confidence intervals. So we spit out here all the confidence intervals for you. We have a 68% prediction interval, a 95% prediction interval, a 95% confidence interval, as well as the raw the R2 value that gave you that. So you can look at that's kind of like information about how good your correlation fit is. And you also have your raw RMS value that was used to calculate the kind of the combination of all three axes. What's your RMS value that is used in the value to give you that regression relationship? And so, they're all nans at the top, but by the time you get the tag on the whale, you start to get these values that are essentially the lower and upper limits. So if your speed is at 0.83, your lower and upper confidence levels are here and here of that speed value, just based on the regression prediction equation. So it helps to give you some confidence in your speed and to be able to do some error checking on the regression relationship. Now that's just on the regression relationship. That error isn't going to account for things like, the whale wasn't acting right and I didn't get I just got a big cloud of dots. It's just the error on the regression. So just kind of keep that in mind when you're thinking about statistics for this stuff. The other thing that it spits out is the speed stats, which is the record of all the different models that are used to actually create those pieces. And so you can explore what those different models are for the different sections. The first one is the first section, the second one is the second section, and the third one is the model for the whole deployment. So you'll always have at least two. You'll have, if you have two sections, if you have one section, it'd be one model and the whole deployment, and those would be the same. In this case, we have two sections, one section, two section, and the third one here. And some of that information is all in the speed stats. You have that, all that information here, where it kind of describes what actually is happening. Cool. Did that answer questions so far, Will? Are we feeling good about that?
Yep. No questions.
Awesome. Cool. So now we got speed, we got pitch, we got roll, we got depth. We're basically ready to save our first version of our PRH file that gives us a basic amount of information here. So this is basically this is it. We're going to start. This is not, we can still do more with the data, and we're going to create still some GPS adding and things like that. But this is their basic function that this is essentially equivalent to what you might get if you're if you're used to working with D tags. You get that kind of basic PRH file. So this is going to recalculate all of our pieces here using our inputted calibrations and all that stuff. And then it's going to spit out a PRH file. And so just as things to edit here, you're the creator of this. So we like to keep track of who created this. So if someone else is using your data, you can go through later and be like, oh yeah, I have to go back and ask Will about this file because I see something weird about it, and why did he make that decision he did about that tag slip? Let's talk about that. So if you might change this to be your own initials essentially. There's also space here to have notes, and that's going to go in an info structure here that's created down here. And the info, so this you could say things like created for tutorial, or you could say things about the deployment. You could say things like, oh, this whale. This specifically about processing usually is what we have in here, but it'd say things like this whale never went below 5 meters depth, and so it was hard to calibrate the speed. So you might say things like that in this information file, in those notes, that you have that as a record for later on. So I'm going to just run this section, and what the output for this section is going to be a PRH file. This variable is listed below in a PRH file. It's kind of double checking your UTC offset. And then it's going to create this PRH file in your main folder here. Now has a PRH file that has the deployment information, the deployment ID, and your 10 Hz PRH file that has all of the variables now in in this variable names. It basically has all of these different variables now that you can use to adjust and get into your data. So that's our basic workhorse script here. This info file structure is one that we kind of come back to a lot. It's just basic information about the tag. So it's going to say things like your UTC offset. What was your tag slip? What was your W change? What was your W file? This is the orientation information about your tag, about how that tag slipped. So all of these things that you can use to reconstruct your PRH file later on. It has things like your original sample rates in there. It has things like your notes that we just said, your tag number, your whale name. All that is kind of saved in that info file as a way to get things later on. Your odd file here, that's your audio rate. That's the sample rate of your audio and the kind of the general information about that audio rate. Yeah, and that's our, it gives you a little information about when that file was created and saves you as the creator, et cetera, et cetera. So that's our basic PRH file. We're gonna switch gears here and talk about how to use that PRH file a little bit next. And then we're gonna wrap this up at the end of the day with some information about how to add in GPS and maps and pseudo tracks and actually make things like a track plot file will be coming up a little bit later on. As Jen's going to kind of introduce us to why we would use track plot files, but we'll start kind of going through these informations now. Any other questions before we transition to that about making this? How were people able to make PRH file. Okay, so one question's coming up is so this get UTC structure, this file is trying to like calculate the UTC essentially. And so if it's asking you, if it can't find that file by itself, it's asking you to find that UTC information spreadsheet. So that is in your CATS tools under utilities. There's this UTC location spreadsheet. So in your GitHub, the things that you're downloading all the time, there's this UTC location spreadsheet, which just has a list of like basic cities with the closest UTC. So it's trying to automatically calculate your UTC information. And it just kind of tells you like, we're trying to calculate this automatically, but you might want to check that because those things change all the time, to be honest, about like where you're, what time zone you're in and how daylight savings time is accounted for and things like that in your local area. So there's this automatic calculation of that. It tries to do that. And if it can't find that spreadsheet, it'll come up with an error and then you just have to input it yourself. So those are different versions that might happen for you. Cool. I'm just going to do, before we move on, a quick poll. I know that not everyone can do polls here, but we'll just do a quick poll of if you are able to have a PRH file, because that'll be good information for moving forward before we transition over to Will. Were you able to create a PRH file? Yes, no, save. Okay. Just launch that real quick. Tell me if you were able to actually save that PRH file all the way through that step as you were following along here. Not very many people, it looks like. Okay, so we'll keep coming back to that file. I'll move that file into the folder for later on. But it looks like a lot of people might have been coming up with errors for this. That's good to know. So I see 27 no's and 4 yeses. So we'll have to we'll pause on that and we'll come back to that and we'll hopefully be able to troubleshoot that later on. For now, while during these talks, I will upload the PRH file I just made onto the server, onto the Google Drive, so you can download that to kind of do the next steps. And the next steps will rely on that info, that PRH file. So you should be able to move on from there so we can finish those and come back to troubleshooting your errors a little bit later on. Cool. I'm going to stop my share here and pass it over to Will.
Yeah, and let's maybe take like 2 or 3 minutes or just a little break if people need to go to the bathroom, anything like that. Yeah, then we're going to move on. So I think Sherelle, how are you?
Present.
All right. Cool. So yeah.
We can take that break. Cool if we need a break though.
Yeah, let's just give like another 2 minutes. Just let people decompress a little bit from the code.
Yes.
Because I think this is going to be a little bit of a left shift.
Can I ask a question in this break?
Of course.
Yeah,
Which might go into what Sherelle's going to talk about, but have you all investigated the idea of like an automatic detector for tag slips, like coding that in to identify it so that you can go in and say yes or no?
Yeah, so to be honest, I've tried automatic things for almost every step, and when it comes down to it, like there's just so much variation, and then all of a sudden you get one weird animal that you're like, is that a tag slip or is that a bump or is that a bad enough tag slip? And when you start having to try to program in thresholds of detection, you just get to like a point where you're like things mess up. And so in the end, what's worked well for us is to have these parts be manualized, and you know that might. If some people have good enough deployments that are always the same, a lot of people don't even have tag slips if they're you know doing a different attachment method. But so for us, this is the thing that works best for us. It's the same.
So what's driving the variability? I guess like I guess maybe I just don't understand the physics that's backing all of this up.
Yeah, the variability in tag slips specifically. I think part of it is depending on where the tag goes on the whale, the amplitude of things like vibrations or jerk signals or accelerometer signals can change and can vary depending on where the tag is on the animal and how the animal behaves. And so when you're trying to like set things like, okay, if you have a jerk magnitude above 4 meters per second, that might vary from one to another. And so like you can see that with your eyes more easily than I can automatically detect it. Like, you know, I'm not saying that there's probably a machine learning algorithm out there that can do this, but that is beyond my pay grade. So if you are interested in getting into that, for sure, I'm happy to like try to implement that stuff.
Yeah, I mean, I'm way outside my lane here talking about this, but you know, I know that they do that kind of stuff for like automatic acoustic detection. So I was just thinking about like looking for shapes, like setting up a detector that looks for a shape.
Yeah.
I know.
Sherelle's going to talk about that a little bit now too, in terms of like event detection and like, so to what degree, like some of that stuff can be automated and some of that stuff, like there's reasons that like some of that might be better to still do manually and what we're using your PRH file. And so I think that's a good transition almost to like to transition over to these guys talking about some of those things.
Yeah. Yeah. So let's maybe start talking about event detection. So I think Sherelle might start. Sherelle is awesome. She's one of our lab mates in the Goldbogen lab. She's a year ahead of me, so she's currently partway through her 5th year. And she's been doing a lot of really awesome work on looking at morphometrics of different whale species, looking at a lot of like scaling relationships. And she just recently had a paper come out looking at scaling of whale filtration, which was really awesome, and using a lot of these tools, obviously, to sort of detect different lunges and detect different kinematics in different places, you know, within the lunge and the filtration process for a large whale. So take it away, Sherelle.
Thank you. Can you hear me okay? Because there's a fan on behind me. Is it interfering with you being able to hear me? Okay, great.
I can hear
Perfect.
you great.
Thank you. Okay, well, hi, everyone. So excited to be sharing a little bit of what I know about the tags. Will gave a perfect introduction, so I won't really go into that more, but I'll just say that the frustrations that a lot of you may be feeling right now about the tags and how the data is coming along are very normal and totally something that we can all understand. We have many little lab jokes about it, but at the end, when you finally understand, it's like the most best accomplishing feeling ever. And hopefully Dave and Will and myself and other of our lab mates can help you all get there over time, because it's totally worth it. And you get to do amazing things, some of which I guess I'm going to talk about right now. And so, well, I'm going to just share my screen and put up a PowerPoint just so I can keep myself on track. And then I'll show you all a different MATLAB script that you all don't have yet, but that you could have, that you could adapt to yourselves. So I'll just begin. Let me share my screen. Will, please let me know if I share my screen well. It's always hard to know. Are you seeing a PowerPoint?
Yes, we are.
Okay, excellent. So this is the thing we're going to talk about today. It's event detection. And so event detection can really mean anything you want, but in the Goldbogen lab, it means going to pick up the tag in the rough ocean, then taking it home and unboxing it, and then somehow getting data out of it where you can identify a point. And so what I'm going to talk a little bit about today is how to get from the picture on the ocean to the far right side. And so event detection can just be anything you want. If you know something about your species and you think it would be identifiable in the tag data, that's an event detection. Do you notice something unique when you watch the videos first? Are you going to look for that in your tag data? That can be an event detection. Did you tag your animal for any specific purpose? That's also event detection. So basically, the PRH can help you identify those events if they have a kinematic signature, which is pretty awesome. So for whales, for rorquals, I mean, I'm sure a lot of you all know this, but we have this really amazing kinematic signature that we can detect. It's the lunge, right? They have this massive, remarkable, rolling, upside down feeding event that we can detect, or we think that we can detect. So luckily, we can use the PRHs to determine whether or not we can detect that. And so what I'm going to do now is I'm just going to stop with the PowerPoint and go over to MATLAB and show you what that might actually look like when you're finished with a PRH. And so I'm going to stop sharing my screen for a second. And so I really wanted to use the whale that we all worked on doing the PRH, but unfortunately that whale did not lunge. So we are going to use a different whale. We're going to use a blue whale. And so, well, I'll just start with that and then I'll keep talking about specific things. I've noticed that a lot of people are having like really specific issues or questions. And so this is something where I'm sure as I'm talking about it, you may have a specific question about it. So please just like interrupt me, or Will, if there's a chat, just like yell at me and I'll switch gears. But so I'm going to go back to sharing my screen. So we're going to go into MATLAB, which you're all super familiar with. And so in our lab, we have this script. It's called the Simple Lunge Detection Audit Script. It's basically a script that Dave's worked on, that James has worked on, that loads of people in the lab have contributed to. And this script, as Will and I have discovered, is actually very malleable, because the first step is to load in your PRH data. So you have to have the PRH ready and done, and you all will have that very soon. And then the next step is where you plot your PRH through time, and then you can move through it. And so depending on what you're looking for, you can change the buttons, as you will soon see, to adapt to that thing. So if we're looking for lunges, we're going to have one button, and that one button is going to identify lunges. But Will, for example, was looking for fluke strokes, and we just built off of this script and worked on fluke strokes. And I was looking for filtration. So if anyone is looking for an adaptable script to do event detection, I'm sure the lab will be happy to share the script with you. That's correct, right? We can totally share this script. Yes, Will's giving me a thumbs up, which is perfect. So I'm going to give you a look as to what that looks like. So let's say we have a finished PRH. We're going to work with a blue whale because you'll see why. But they are, you all know, the biggest of all the rorquals and the most cool. And that's my own little bias. And so I'm going to run this section right here. And I'm going to select my PRH. So here, what you might see in this pop-up window is just a huge list of PRHs and lunge files. It is for something I'm working on, but I'm going to navigate to the whale that I'm looking for. So first I'm going to select the PRH that we made, and it's going to get uploaded into MATLAB. And so it just popped out some useful information just about when the tag was turned on and how long the tag was on the animal for. Sort of the same thing actually that you get straight out of the PRH maker. So then we're going to move forward and load the data. And so this is the plot and process section, which basically that's the really fun part. That's the adaptable part. What it's going to do is it's going to pop up the PRH over time, and you're going to be able to navigate through it and select things. So let's do that right now. And so hopefully you all see a big new pop-up window with the name of the animal at the top and 3 panels. Will's giving me a thumbs up. Perfect. Okay. So if everybody could take a look at this and let me know, perhaps someone chime in, or I'll just wait a couple seconds for everyone to take a look. And hopefully what you will see is some very identifiable thing that is occurring throughout time. And that is more or less the idea behind this event detection thing that I'm talking about, that you're seeing this repeatable, remarkable thing happening. And I'm seeing the chat. I don't know if anybody is seeing things, but I'm going to tell you at this point that basically you can see these decelerations. You can see these really sharp decelerations in speed. That's what's on the bottom. You can see the pitch going up consistently. You can see the roll consistently. You can see these multiple consistent events occurring. And so you could be wondering what they are. And so you could approach this in two ways. If you don't know what you're looking for, but you see a consistent event, you could mark it. And so based on my script, marking it is a left click. And so this box pops up. We know what this is. We know that this is a lunge on a blue whale. And so we just see this blue whale doing lunge after lunge after lunge, which is pretty amazing. And so you can move these lunges around. You can, so these are if you can see on the left-hand side here, there are a bunch of controls. So you would be able to change those if you were using the script. So if you were looking for 3 things, you could change it rather than left click, likely a lunge and maybe a lunge. You could change those up to be, you know, a change in pitch, a change in roll, and a change in heading if you wanted to break it down that much. And yeah,
Sherelle,
yes.
I have a quick question, and then there's one in the chat here.
Okay.
So if you could only look at one of these 3 subplots, which would be the most important to you if you were looking for lunges?
If I was looking for lunges, I think that the most important thing, that's a really good question. That would be very hard for me to answer now because I'm so spoiled and used to using all 3. So this will be a hard question for me to ask. I would say that based on my pre-existing knowledge that a lunge is a very intense increase in speed and then a sharp deceleration, I could be convinced, I could probably use the speed alone. But if you didn't know in advance what that signature was, I would be very cautious of using only one plot, because sometimes there are peaks in speed that coincide with surfacing behavior. And so then you would be mistaken. So a really good thing about this script is that it plots all 3 and that you get a triple confirmation. And later in a couple slides or soon, whenever I run it, have I run out of time? I've run out of time, haven't I?
No, keep going.
I'm okay. Okay. Anyway, eventually, when you all manage to stitch together the videos and you have this beautiful plot moving along with the videos, you'll also be able to use the videos to confirm what you're seeing. So I think I'll just move on to that because I was supposed to keep myself down to 15 minutes. But so hopefully you can see that the PRH, once you have it made and you can look through it and you can go forward and backwards. So now I'm moving forward in time. I clicked away from it. I'm going forward in time and backward in time. No, I'm not. I messed it up. What just happened? Oh, and this is the end of the deployment. You can see the tag moving like vertically up, like no animal would ever do, and then floating up at the surface like this. So I guess essentially what I'm trying to show you all is that this script can be very practical for looking for things that might exist already or things that you're looking for. So there's that. And I could, if there's time, I can show you a video that proves this more or less. Will, was there another question?
There was a question about rolling. Basically, you know, do they actually roll right and left each time, or do they switch? And Dave had a good answer there. He linked one of the
papers.
Yep.
Okay, perfect. That would have been my answer as well. Yep. Which is a pretty cool finding. So that's another thing. Like, yes, you can do this amazing event detection and you can look for something unique, but then the more you're able to dig into something, the more you're able to find these interesting, deeper ideas. So yeah, we located the lunge, but now we've also identified the fact that they tend to roll a certain direction, or, you know, they make 2 turns before, like bubble netting, which Jen might talk about later. Like they do 2 of them before they lunge. Like that is something you can do from this event detection. And so the PRH gives you an understanding of the kinematic data and like how the animal moved. But I find that event detection can give you like also part of the ecological context and the physiological context. So that's why I really love it. This is a video because it's fun to watch whales. So you'll see in this video that just as the whale gets the fun dolphins, this is a great video. Maybe Dave has shown it. You can see that there's this sharp deceleration in speed, which here is green. And there's that high peak and jerk. And so the video, when you align it with your tag data, really, really helps you with this event detection. And so if you're watching your video for the first time and you're not really sure what you're looking for, then I would say watch the video with the PRH at the bottom, and that will help you locate kinematic events, which I think is really cool. And so please shut me up when you want me to stop, but I'm just going to keep going. One of those things that we were able to do is the filter time. So Will very kindly, what's that called, boosted my paper, but this was a big part of that paper, which is basically we made this identification of a lunge right here, which is what I just showed you in that event detection. But what it allowed us to do was make further detections. We just modified that script even more so we could click in different places. So we could click where the mouth opened, and then we confirmed it with the video. Like at this peak in speed, we see this consistently in the kinematic data, but do we also see it consistently in the video? In fact, yes. So you get to, and then we clicked again, mouth closing. We saw it in the video, we could see it in the kinematic data. And so we could assess that this was the amount of filter time. And then we could actually watch the ventral groove blubber deflate over time because of the video. We could see it align with this very flat line in the speed and in the gyroscope and in all of these settings that we decided were important for this event detection. And then we could determine when the end of filtration was. And so based on that, we got to publish a paper, which is pretty cool, which showed that the bigger you are, the longer you filter, and you do that exponentially so. And all that really to say that event detection can lead to some really interesting insights about the animals. And even if you don't know what event you're looking for, the script is malleable enough that you can work through it slowly to figure out what your event might be, and then go back and add it into the script. Yeah, happy to talk about it more, but that's about it.
Awesome. Thank you, Sherelle. I think maybe we have just a few more minutes before Stacy is going to be talking to us about the animal tags, D-tag tool sets. And so I'm just gonna really quickly go through a few of the other types of event detection that I've been kind of working with. So I'm gonna, let's see, we're gonna start with a fun one here. So what do you usually use for detecting flipper strokes? So that's actually what I'm about to talk about. Here we go.
That was a perfect segue.
That's perfect. So, okay. Dave mentioned a little bit early on that we had a deployment that ended up on the tail of an animal. So I'm actually going to show you a little bit of that video. So, and this kind of gets into a little bit also of like, you know, tag slipping and things like that. Because again, they're attached with suction cups. So they're not staying on all that great every time. This one went on the left side of the animal. This is a humpback in Santa Barbara. And so you can see kind of the left flipper there. And then it kept moving, and you can see it really slipping down. Now it's sort of behind the urogenital slit. And then it sort of pops onto the other side there, and it's still sort of moving around and doing a lot of activity. And then at some point here, and then it sort of performs magic and disappears and then reappears on the tail of the animal. So you're going to see we have our little magic trick right here. And now all of a sudden it's on the tail, and it stayed on here for 45 minutes, which was pretty incredible. And the, you know, the whale's kind of swimming along, but you can really see when it stops, you can see, you know, the entire body of the animal from the perspective of the tail. And so in terms of, you know, if you're looking for tail beats, you know, flipper or in this case, fluke strokes, they're pretty easy to pick out on something like this. Especially, this is like the most clear example you could get because it's literally on the tail. But these signatures, these sort of, you know, sine waves that you get that sort of correspond to active swimming, we see those even if the tag is on the body. So what I kind of did for my first chapter was look through and say, okay, you know, how does the frequency of that tail fluking change with body size? And the nice thing is with all these different tags, I was able to sort of come up with a little detector that could look through and say, okay, during these sections, the whale is fluking, and these are the different fluke beats, and this is how long each fluke beat was, and so I could get the frequency from that. And I'm just gonna move forward here a little bit because this is kind of fun. You're gonna see the whale is actually gonna lunge. I'm not sure if the video is a little bit choppy, I apologize, but for a moment here, this whale is gonna, and you can see this sharp drop off in speed, which is what Sherelle was talking about. So we're gonna see the whale goes, and then it lunges. You can see it's now lunged. You can see that ventral groove blubber that Sherelle was mentioning. So the whale has now engulfed all this water and prey. You see it's just kind of gonna sit here and it's gonna filter. You can see some little fish coming by, and we're gonna have a fun view of the whale as it sort of lifts its tail into a perfect position so that we can actually see it. Let's see, right, where is it? Right here, I think it's gonna do it. Yeah. There it is. You get a really clear view of the animal from the tail. And that is actually the image that I have on the little business cards I've made, because it's the coolest thing I've ever seen. So that's one fun thing you can do. You can do fluke beat detection. And there have been a lot of different ways to do fluke beat detection. Mine is a little bit new, and I sort of came up with it based on some old methods, just because I wanted to know exactly what was kind of going on under the hood. But yeah, there's a bunch of different ways people have come up with to figure out when an animal is swimming, essentially. And then one other thing I want to talk about really quick is bubble netting. So Sherelle mentioned lunging, and that there's this really clear kinematic signature for lunges. So I just want to show this video really quick, because even just right there, what can you guys, what looks weird about this data? Or what looks unique about this data, if anything? Thinking about those bottom subplots. Me
Heading?
a little bit. Yeah.
The heading?
The heading, yes, the heading. So this is on an animal up in Alaska that we tagged last year with Andy Szabo and Lars Beider's groups. Some of our other collaborators. So this was a really, really fun project to work on. And what we're going to see here is the animal is going to do something pretty cool. It's going to start in a moment here. Come on. Come on. The anticipation, there it is. It's going to start blowing bubbles. So it's going to start creating this bubble mat. And you can actually see that flipper really, really turn as it goes into this really tight rotation. And so what we're seeing here is a really cool example of where you can use both the camera and the video as sort of feedback and validation for each other, right? So we're using the camera to say, okay, we know exactly when the whale starts bubbling, right? Because we can see it on the camera. And then we're using the data to say, oh yeah, we know the whale is turning, and we know it's turning in a specific direction because we can see the change in the heading. And this is really cool because you can go through, even just from sort of the broad overview of the data, you can see when they're doing these bubble nets because you get these crazy signatures in the heading. So even without looking at it super deeply, you can get a really good sense of what's kind of going on there. Yeah. So that's just, a few other ways that you can perform some event detection and some other things that you might want to detect. Yeah. And so I think on that note, we will move forward and have.
Yeah. Thanks, guys. That was really cool. I just want to jump in to be able to to say that there's some cool stuff going on in the chat right now with people talking about how do we apply these to our own data sets. And that exactly is a great transition to what Stacy is going to talk about next, which is some of the great tools at animaltags.org that do really take these PRH files or even before the PRH files and helps you create really well filtered data and really well just kind of structured data, and kind of was the pioneer. Stacy and Mark and others have really been kind of the pioneers of developing these MATLAB based and other platform based tools. So MATLAB has been driving you crazy all week. Stacy has been working hard to adapt these tools to R and other ones that I can't even remember right now. So she'll talk about all that and give you guys a really good introduction to that stuff now. Will, I didn't mean to cut you off. Is there anything else you wanted to say in that regard?
No. Yeah, please take it away.
All right. Well, that we'll turn it over to Stacy.
Thanks. And first I can just say I'm super excited that this workshop is happening. I haven't been able to be here live all the time, just juggling other stuff, but I've been catching up at night. And it's fabulous that this is happening, and I appreciate being able to be here also. Let's see, I haven't shared my screen in Zoom for a while. So I'm slow. Here we go. I think eventually this will work once I can get to see what I need to see. Sorry, everyone. Incompetent professor here. So I will try to tell a little bit about this project that we finished it up about 1.5 years ago, maybe. But as many of you already know, if you came to any of our workshops or have checked out our web, it was really like 90% finished, which is unfortunate. So we're hoping that we're going to get a little bit more funding to do that final 10%. But the idea was to create some more user-friendly tools and training materials for working with high-resolution movement tag data. And the original team was Mark Johnson, and then Katrina Harris, my 2 students, Yiju Oh and David Sweeney, and then Tiago Marks and Renee also helping out. And in the next iteration, Lucia Martin Lopez and Alex Shorter are going to be working with me and Mark to hopefully go the final mile on this. So the idea was that we were going to take Mark's tools that were made for D tags, but they were kind of and had a really steep learning curve because they weren't that well documented for working with data from tags that collect movement. And the goal was that we would have something flexible, open source, workable with multiple tag types, not only D tags, and would work on Octave was the other one, Dave, and R. And we've had moderate success getting it to work on R. Maybe I'll have a chance to talk about that a little more. We'll see. And then we also wanted to design and do workshops to teach people how to use these tools. And hopefully in the second round of the project, we're going to make online education materials that you can do like self-paced on your own, which I think will be a huge addition. So we were making some new tools. We were also translating back and forth between MATLAB and the other platforms. My students did a ton of work improving the documentation, which is crucial for learning it. And then we did, and the people in the workshops also tested them. So we have this animaltags.org website that you can check out. It needs reorganization. That's hopefully part of Tag Tools 2.0 project as well. But everything is there. And we also have a GitHub repo that has all of the MATLAB, Octave, and R tools in it. And then we did a few workshops so far. So we did what we said we were going to do, more or less. And we have 4 different sets of tools. I haven't put like an extensive catalog of everything that's in there in this talk, but I can answer questions if it's of interest. So the first phase is kind of like reading and writing your data, calibrating it. So getting it from like voltage units to scientific units, some of the things that you've been doing now, validation, making sure that all the calibration went right, and that and then processing and visualization steps. Also some of the things that you've been working on this week. And then we have a few tools related to statistical analysis. So I can show you a couple of the things that this can do. So we can read in data. So the code that I'm going to show you in this little mini demo is our code, just for a little change, but you can do all the things that you can do with this toolkit in either R or MATLAB. So you can read in data sets, and we have devised a file format that is an NC file format. That's a standard scientific file format for combining data with metadata, which is what we wanted to provide for, not necessarily for working with your tag day to day is not always the simplest, but for being able to archive it, having the metadata attached to it, like what species was this, when was it tagged, where was it tagged, all that kind of stuff that's not in the tag data itself. It's really helpful to have attached to it. So we have tools to read in and write and create these NC files that are the archive ready format for a tag. So you can read it in. Something weird is going on here. Yeah, my thing is broken. Okay, that's awesome. Let's try a different way. If this doesn't work within 30 seconds, I will abort. I just want to make it a little bit bigger for you. Can somebody tell me if this isn't big enough to see? It's kind of okay. So I can.
Yeah, it looks good, Stacy. You're doing good.
Okay, thanks. I can read in a data set and all right. I do know what's going on. I switched computers because I was afraid on my other computer that that I didn't have Zoom working, screen sharing working properly. So this is quite sad for me that my little demonstration is not working as well as it should, but I'll skip ahead a little bit. So you can read in data and save it. Let me see if any more of this. The objects that the data is stored in, they have the data matrices in them, but they also have metadata, like what's the sampling rate? What kind of sensor was this recorded with? That kind of stuff in it as well. And you can investigate that information if you want to. And there's also an interface where users can enter in metadata for the tag and sort of fill out more details about where the tag was deployed and enter all that data to be attached to their data for archiving. We also can do some of the things that you've been doing with Dave and Will this week about calibrating. Like one of the things you did was fix the pressure sensor data where it's sensitive to temperature or if there's an offset from the surface. And so we have simple functions like fix pressure 1, and you give it your pressure data and your temperature data, and it'll do that correction for you and spit out the same format of object except for with the pressure sensor corrected. You can also do things like crop your data to specific time points. Again, with a simple function, you just tell it you want to crop, you give it the data that you want to crop and the times that you want to crop it to, which can be really helpful, especially when you have really huge data sets. I'm working with some now that have like 12 days of data and it just doesn't fit in memory very well. So cutting it down is helpful. If you can't see the graphs are not very exciting, but we do have a function that makes it really easy to make a graph that shows multiple time series. Here's an example of the kind of graph that you can get out, and it can be shown on the x-axis either time since the start of tagging or date times, and it aligns all these axes for you and attaches them to each other and lets you interact with them. So it's not necessarily publication ready figures, but it's really great for exploring and interacting with your data. You can also compute things like acceleration based metrics like JERC and MSA if you want to look at those, and so compute those from your acceleration data and then graph them. You can see it didn't take me very much code to compute all those things and make a graph of them. Can be kind of nice. Let me keep going, maybe. The last couple of things I wanted to mention that we can do, we have a few like automated detectors and processors that might be useful to a lot of people, especially if you're working with marine mammals. Something you often want to do is detect the starts and ends of dives and then compute characteristics of them. So we have a function that will detect when a whale submerges and gets back to the surface. You can set like a minimum depth that a dive might be and how close to the surface it has to get again to end a dive. And then for each of those, you can compute summary statistics like what was the overall deepest depth, how long was the dive, and a bunch of other standard dive statistics can all be computed for you pretty automatically. And then finally, we have a few tools for some statistical analysis that are not easily provided elsewhere, like making dead reckon tracks, something called a rotation test for event rates in time series data, Malinobis distance if you're interested in that. And again, these are all like simple functions where you just have to say what your data is and any other little bits of information that the test needs to know, and then we'll nicely split out for you some answers there. So that didn't go as well as I might have wanted it to. We have done a few workshops to try to help people learn the tag toolkits, and we've included some lectures, and the slides for those are online. Computer practicals, and those are online, and tag practicals obviously don't translate online, but all this stuff is available to you if you're interested in checking it out. I suppose maybe I should make this bigger for you. But there were a couple issues with our original project. The interface for adding metadata to archive ready files, and then the process for submitting those to the archive, especially if you're using the, if you're part of the US Navy funding system and you need to submit data to the ATN DAC for archiving, it just wasn't quite ready for this kind of tag data until very recently. Now it finally is, and so we're trying to work with them to make that process easy. R is not, it's really hard to get all this stuff to go in R. So the reason why MATLAB is worth learning is because it's super fast at doing math with huge matrices. R, not so much. And we've conquered some of those problems, but not all. So that's another thing we're hoping to improve on. And then we also just put way too much stuff into the tag toolkit. So there's all these fabulous tools that you can do processing and statistics right now. But some of the tools for like reading in data from the different tag types are not quite there yet. And so if you can't actually read in your data, the whole toolkit is useless, which is why we're hoping to continue to work a little bit more on this in about a year to come. We're hoping that we'll get some funding, and then we'll be able to have a software engineer to help us to get everything really up to snuff, especially the reading in data part and the tag frame to whale frame conversion part, which you learned about some of the nuances of this week. But there are tools in the animal tag kit for doing that as well, and we're hoping to improve them for all the different platforms. So like for Mac versus PC, and also R versus MATLAB. I think that is more than enough that I wanted to say. Someone asked if we recorded the lectures from the workshops. We didn't. It was, the last one was in Barcelona. It was kind of before the time when we would have thought that that was a good idea. I think if we had given one later, we would have realized that that might have been a good idea to try to record, but we didn't. But that's part of what we're hoping to do going forward. So a lot of the lectures will be much the same, but they're just going to be split into smaller chunks, and then we'll have recordings, and there will be an organized sort of task-based interface on the website. Right now, it's kind of like we just took everything we ever made and dumped it into a pile in the website. It's not very user-friendly. But we want it to be like that you can go there and you can say, I really want to learn about tag frame to whale frame conversion. Like, okay, here's the 3 videos you should watch. Here's the practical you should do, like that kind of thing. All this stuff is there. It's just that figuring out how to use it is currently a catastrophe. So we're hoping that we can just take that the final mile and make it easy to use all of these things that have been created. And I love that people like Dave and Will have like taken some of the tools and like integrated them into their work. Like that's exactly the reason why we try to do this project, and what we're hoping will happen, so that people don't have to duplicate effort and like recreate the same tools. The standardization and the sharing is super helpful.
Yeah, I think that's a huge point, Stacy, that I would just totally echo. And that, like, you know, if Stacy's workshop had been available to me 6 years ago, then, you know, like I created a lot of these things on my own, and then we had to like go back and integrate the better ones that Stacy's group did to be able to like put into our tools. So like and we're just basically recreating things. So a part of this workshop, a lot of it is to like try to like put it out there so you guys don't have to recreate the wheel that other people have done and try to share these resources. And so, and a lot of that comes to exactly what Stacy said in terms of like importing your data into the reference frame. Like that's kind of one of those first steps, and getting that first part to work would be awesome. Yeah, Stacy, I don't know if you want to talk about Python in general.
Yeah.
Like Danuta just asked.
Yeah, it was the next one on our list when we were deciding what software platforms to use. MATLAB was obvious because Mark's tools were already in MATLAB. And then we thought, what else should we be using? And the options that seemed to make sense were R and Python. Because I know R better, and there was no one on the team who was really keen to use Python. And also we just feel like more people in the field are also using R alongside MATLAB. And at least 4 years ago, fewer people were using Python. So my sense is that will probably change, and I have high hopes that eventually these tools could also be translated to Python. But as you can see, the R version is still not totally complete, and so it didn't make any sense to divide my attention to like yet another language until the ones that we have committed to are working well. But I think that Python would be fast like MATLAB in a lot of ways. I think it has good potential to try to do that at some point, especially once more of us start using it.
That's awesome. And we will talk a couple of R tools that have been developed by Max Sapansky as well, that we'll talk about tomorrow to kind of throw the other R tools out there for people who love that stuff. Any other questions for Stacy? That was super, super helpful. Like every time I see that you guys do the work you guys do, it's awesome. So, any other questions for Stacy?
Hopefully in the next 12 months or 18 months, we might have our website like dramatically improved. I know I keep saying that and not doing it, which is why we're trying to get another round of funding to actually do it. And also, I think I have a pretty fair excuse with the whole pandemic that has happened, that things got delayed a little bit more than they should have been. But we, the whole problem with tag tools is that everyone wants to analyze their tag data and nobody really wants to make the tool. Like, it's not the fun part. But at the same time, it's really important for democratizing the process and making it easier to learn. So we're trying to make progress. And if anyone wants to help in this project or has contributions or wants to join the team, we would love that beyond words. So thanks for the opportunity to be here too.
Thanks, Stacey. Yeah, and thanks to just points out to thanks to all of you guys for being here at this workshop as well, because what you're doing is also helping us make these tools better for everyone to use. And so I know you just want to get into your own data set, and it's really helpful to kind of hit these errors that you guys are hitting. So thank you for doing that. Thank you, Stacey, for being here. And I'm sure everyone is applauding rapidly, really loudly for you. So thank you for being here. On that note, we are going to transition and talk more about some of the using tools. We're going to transition back to video here a little bit. I'm going to share my screen for a second because there is some tools that I was late in uploading, and I'm sorry about that. But there are some tools here in the Google Drive, either from the website or the Google Drive link, or just from, if you have the Google Drive file stream, in the workshop materials, in day 4 in the workshop materials. Day 4 already, you guys are troopers. There's 2 new folders in there. This trackplot folder is already available in the example data folder. So if you might already have that in your example data, but the Boris presentation resources were new, and I just uploaded those up there. And Sarah's gonna go over some of these next. So if you have a chance to download these resources from the Google Drive, you will be happy that you did. And with that note, I'm going to pass it over to Sarah, who's going to talk a little bit about using these video resources and like taking these. How do you like deal with these large video files and knowing what things are? And this is a cool tool called Boris that she's going to tell us about. So I will stop my share and let Sarah take it over.
Perfect. Thank you, Dave. I don't know if you guys have the actual. We're going to be doing an activity with you guys where you guys can actually practice auditing videos yourself. And the download is super easy. I'll put the link in the chat. It's a pretty small package. So if you want to try that out on your own, feel free to download the software. It shouldn't take long. So by the time we get to the activity, it should be all ready to go. But in the meantime, let me share my screen. All right. Okay, beautiful.
Sarah, I didn't do a great introduction for you guys either, but maybe you can introduce yourself and Nicole and talk about what you guys' role is and where all this comes from too.
Yeah, sure. So yeah, Emily will be joining us a little bit later, but all of us, and then Sarah and Ariana weren't able to make it today. But we're all RE students, so we do a little bit more of the, I'll say, less technical stuff than the Goldbogen guys. But yeah, so we'll get to the research applications in a little bit. My background is actually more in acoustics than in the video auditing side of things. Nicole, do you have anything you want to say about yourself? Oh, I think you're muted. Oh, shoot.
Hi, I was going to introduce myself. I'm Nicole. I started off in Ari's lab as an undergrad, and now I'm currently at the University of St. Andrews doing my master's in marine ecosystems management, but still participating in some things here and there for the BTBL lab. So happy to lend a hand where I can. I'll let you take it away, Sarah.
Thanks. Yeah, all right. So Boris is a really cool software that you can use for video and audio processing. We haven't used it for any of the acoustic analysis, but if you do want to throw in the hydrophone data into here as well, it's a pretty great software, so knock yourself out. Unfortunately, we won't be able to give you any tips on that end, but we'll just be covering the video here, and it's still really cool. If it'll let me move. There we go. All right, so while you guys won't have it set up quite yet, this is what you'll see when you first open the software. It's super blank. You've got your kind of standard tabs up at the top, and then the controls at the bottom. I'll go over it later, but those really have to do with navigating through those video files. And I'm going to be talking about templates versus kind of creating your own templates. I think I reiterate this a little bit later, but for the sake of kind of translating the terms that we've been using earlier, like throughout this workshop, to the kind of more specific terms, you can think of like templates, and templates are basically a form of a project, and projects are synonymous with your deployments. So essentially for each deployment that you're looking at, you're going to have an associated Boris project. So all of that information should be consistent in terms of the deployment date, tag number, things like that. And then within those projects, so associated with those deployments, you'll have your separate video files. And when you're auditing the video files, you'll do that in separate observations. So essentially template, project, observation, those all have to deal with just your different deployments and then the video files within those different deployments. I'll restate that again, but just so no one's confused. So looking into kind of the more specific controls just within the really basic Boris interface, you have kind of just quickly navigating through the videos. Unfortunately, there isn't a like scroll function, so you can't scroll through a video like you can in like QuickTime Player. But that is kind of good in some ways because you don't really want to be missing anything. So the best way to kind of go through these is once you have your video file uploaded, you'll just click play. It can be a little boring at times. You can like skip through frames, things like that. And when you're seeing those kind of behaviors that you want to mark, it's really helpful to be able to use over here in like the section 2. You can click that the frame by frame mode and then navigate in a really, really small scale to make sure you're getting exactly the beginning of a point event, things like that, just for kind of that consistency throughout your project. You might decide within your protocols that you don't need it to be exactly when the behavior starts, but that's kind of an important to control if that's really something that you're interested in, and it gives you a lot of kind of oversight in terms of the audits that are being done on your data, especially if they're being done by different people within your group. In these kind of yellow boxes, you have kind of adjusting the speed of the video, so you can make it go a little bit faster if you'd like. This can be a little buggy depending on the length of your video file. And then you do kind of want to avoid the previous and next media files. Those will jump you between observations. And if you're just working on one, you don't necessarily want to be navigating between different ones, but it's important to have once you have all of your observations uploaded within your project. And then over here in this last box, we have the plot function, which is really, really cool. You guys might be able to play around with this a little bit once you've finished your little video audit, but it's really cool because Boris will automatically show you kind of the frequency of different behaviors. You can select which ones you want to look at within your ethogram, which subjects you want to look at, things like that. And you can get some really interesting insight within those video files, just in terms of like how frequently are we seeing lunge feeding, things like that. And it's along the time axis, which can be cool. And I do believe you can export those as well to use them in different places. All right, so to open up your template, and again, your template would just be a project that you've created, you've made your ethogram, things like that, and then you save that as its own like separate project. That way for each new deployment that you're working on, you can keep all of those variables consistent. So you're gonna wanna make your own template in some capacity and then save it so that for each deployment you're looking at within whatever kind of research project you're looking at, you'll be able to keep those consistent, and you won't, more importantly, you won't have to make a new project every single time. I think you would absolutely go crazy trying to do that. But it's super simple. You just click File, Open Project, and then you can navigate to wherever you keep your template within either your computer or an external hard drive. You can select that and get started. Over here, you can see above Open Project, there is New Project. If you want to create your own project template, feel free to open that up. It is, especially when you're starting out, it is helpful to look at template or projects that have already been made, just to give yourself a sense of how you want to structure that information, things like that. But if you really do want to just fully dive in, New Project is a good way to kind of like familiarize yourself with the Boris interface. Regardless, once you've selected your template, the most important thing you want to do is not overwrite your template. And the best way to do that is just to save it as a separate thing. And that will immediately, once you've done that, you're no longer going to be editing your template. You won't have to reopen this new version. It will just kind of do that for you. But this is super important. You don't want to end up halfway through your auditing and realize that you've just overwritten all of your main template. And the way that we kind of recommend you do this is to keep the project name consistent with the deployment name. So the way that we usually keep that is the species, 2-digit year, 2-digit month, 2-digit day. You could make that 4-digit year, it's up to you. The tag number as well as the location. And this is going to vary depending on kind of like what your lab is looking at. If you only work with one species, maybe you don't need to include that, things like that. But it is usually better to keep it as specific as possible. That way, if you're sharing data or something like that, everything's consistent and everyone is going to understand what exactly that project is associated with. So you can see here, the example would be for a minke whale. You've just got all of that information right there. And then when you're going back through either your CADS data, things like that, you can see that consistency across those different platforms. Once you have all of that set up, you'll see the actual ethogram and subject list here. So this is, I believe, an engulfment template. And you can see you've got the keys, which correspond to the keys on your keyboard. The different codes, those are just kind of like a description of like what that behavior actually is. So you can see here filtering, breaching, things like that. The type of event is either going to be a point event or a state event. Point events, you can see here like a feeding lunge, that's just happening. There's like a distinct moment where that happens, and then that lunge is kind of over. Versus a state event would be like filtering, where it might take a little bit longer depending on the species you're working with. And those are kind of up to your discretion, but really important to make sure that you're keeping consistent within kind of your different projects. And then the ethogram, so essentially this first category is your behaviors, so whatever you're marking. And then the subjects list is going to be which organism you're actually marking those behaviors for. So you're mostly going to be sticking with the focal animal. That's going to be the animal that you have the tag on, and kind of focal animal, tagged animal, and conspecifics are usually like a good 3 to keep in your subjects list. Everything else you can kind of change depending on the environment that you're looking at. Some Some species might be interacting more with pinnipeds or birds versus other whales, things like that. So that's up to your discretion. It really will change depending on your data set. Broader is generally better, especially if you're making like a general audit template that you just want to be able to smack onto anything and then edit depending on the specific questions that you would be answering with this data. But back to the ethogram, modifiers are really helpful. It lets you essentially clarify the different behaviors that you're looking at. So I think within your activity, you'll have 2 different templates that you can look at, and I'll get to this a little bit later. But in one of them, you can see that you can really specify, like, it's a feeding lunge, but is there any kind of rotation? Like, what is the whale doing within that feeding lunge? And then you get a little bit more specific info for your analysis of like, what does their behavior really look like on this kind of broader scale. And then the categories, again, are up to your discretion, but you'll be able to play around with all of this on your own. So then once you have your project all set up, so that's everything for this deployment is all ready, you'll be able to start that observations. That's specifically for a specific video file. And to get this all set up, you just go into observations, new observation, and it'll pop up this window for you to input more info on. Your ID is, again, really important to keep specific. So you'll want to include all of the same information you had for that project name, as well as the video file number. This might not seem important, but once you have all of your observations complete, you can look at all of them together, and you'll be able to distinguish which observation correlates to which video file. If you have a really short deployment, you might not need to do this because there might just be one video. But generally, it's a good idea to keep this and keep it in that kind of like 2-digit format just in case. The description here, you could enter information when you first start this out, but generally it's a better idea to just kind of include a brief summary of what happened within that video file once you've completed the audit. And that can be really brief, just kind of, what the animal was doing. Maybe it was lunge feeding for the first 15 minutes and then, split off from the group and just kind of logged for the rest of the video, things like that, just so that when you're looking back at the audits that you've done, you don't have to open them back up and look at those events. You can just get a quick idea of what happened and move forward from there. And then to actually import the videos, you're going to go down here to add media, and that'll prompt this other window where you can select which video file you want to include. And then once that's up there, I personally recommend saving immediately. You don't have to. You can go straight into starting the observation, but Boris will crash fairly frequently. So it's a good idea to get in the habit of saving very frequently, just so that doesn't happen. And if it does, it's not a major catastrophe for your work. It's not necessarily something you should completely worry about all of the time, but if you can save every couple minutes or so, that's a good habit to get into. All right, hopefully I'm not taking too much time with this, but if you do decide to save immediately, the window will go away. Don't worry, you haven't lost your work. You just have to go back up into observations and click observation list. That's where you're going to find the observation that you previously set up. This is also where, if you have multiple observations, you can navigate between them with this function. So let's say this theoretical deployment had like 5 different videos and I've completed all 5 of those audits. You'll be able to see those 5 different observations within this list. If you kind of toggle to the right here, you'll be able to see the description there as well. So you can kind of check in on what happened within this deployment really, really quickly just by opening up that project. All right, so now you're finally able to audit. You'll see your little media window open up here. Boris does have these funny little kind of spaces that it recommends you put things. I personally recommend keeping your media file out of those windows just because it will kind of cramp the video space. So if you keep it outside of the interface, you have a little bit more room. You can see your ethograms and subject lists really well, as well as kind of give yourself enough space to actually see what's going on in the video. And down here, at kind of at the very bottom of this window is the events list. So when you're marking those behaviors, they'll show up down there and you can see kind of what behaviors you've already marked for that observation so far. And don't worry, if you do mess up, like, you know, it's not exactly at the start of an event or something, you can just right click on that event and you'll have the option to edit it. And you can change the time, you can change like what specifically happened, you know, without having to worry about getting it perfectly right the first time. So don't worry. And yes, remember to save as you go. Okay, so now it's your turn. So if you have the software all set up, there will be those two different groups for the breakout room. So if you're in a breakout room that has an even number, you'll be looking at a 1-minute clip of a Monterey Bay humpback deployment. And then if you're in an odd numbered group, you'll be looking at a Stellwagen humpback deployment. And we have included 2 templates for you to look at. Go ahead and open those up. We do recommend also like maybe watching the video through once since it's so short, and you can talk with your group members about what behaviors you want to include in your audit, as well as kind of if you want to use one template over the other one, or if you want to kind of build your own based on those 2 templates that we've included. None of those options are right or wrong. It's all up to you. But it'll give you an opportunity to practice using this software. There is also a resource guide that goes through all of the steps. I know I kind of rushed through it because I didn't want to cramp your time for this activity. But there you'll be able to see all of the different steps, just super basic. There is definitely more to Boris, but we don't want to overwhelm you guys here. And if you have any questions, you can just pop back out of your breakout groups. We'll be here, or you can ask for help, and we can kind of give you any troubleshooting that you need on this process. But we do have a couple of questions that you want to think about. So you can read through these. They're also in the activity resource sheet. So don't worry about remembering these. But yeah, they're just really good questions to think about, even on your own after this workshop, if you decide to use Boris for your own purposes. And then once we come back as a group, we'll be able to discuss together. So Dave, I'll let you take over again. Oh, no.
Yeah, well, so what we'll do is we'll split up. I'll send you guys to breakout rooms, and then you can use that time. So Sarah and Nicole have put together, they're pretty awesome, just like a series of worksheets there to kind of work through Boris and get a sense of what Boris is going to do. We have about, we don't have a ton of time today, so we'll take about 15 minutes, and we'll come back at 12:05 to move on to the next piece. It's all the data and information is in the Google Drive folder that for the day 4 website. Sarah, are there videos in there too?
Yes, the video files are in there.
Video files are in there too. And so we'll take that, and then Sarah, how much do you want some time to go over it when they come back, or is that safe?
Yeah, that'd be great. I know we're a little over time schedule here, but yeah, just like a quick discussion.
Okay, so let's come back at 12:05 and take a break if you need to, and look through those activities as much as you can. And then we'll have a quick Boris discussion then, and then we'll move on to some TrackPod and finishing up the PRH files after that. So we'll send you to breakout rooms. I'll just assign them randomly again today, so you might have to introduce people to yourselves. But that was an awesome introduction, and then there'll be some cool information there, and then we'll come back and discuss what you guys can learn about Boris. And if you have a chance to download it, play around with it, and then come back with any questions, Sarah and Nicole and Emily can answer those questions. Thank you guys so much. That was really awesome introduction. There's a really cool. Cool, we'll give people a minute to show up here. Cool. So hopefully people got a chance to download and play with that software a little bit. It's a pretty powerful thing and pretty cool way to kind of keep track of your audits and to be able to transfer them between people. I did see some questions pop up, and so maybe we can ask those in terms of the big big group here too. We'll basically take about 5 minutes just to kind of answer questions and have a little discussion right now with Sarah, Nicole, and Emily. And then we'll do a little bit of ecological applications of Boris. We'll have Sarah, Nicole, and Emily come back tomorrow morning first thing and do a little ecological applications of that as well. So we'll take about 5 minutes for a little discussion here, and then we'll switch over to Jen after that. So I'll turn it back over to Sarah and see what you guys got.
Sweet. Nicole, do you actually want to take this one? I don't know if we have.
Sure. I guess just relating back to Sarah's questions that she brought up on the slides, if anyone had any points to bring up, or if anyone ran into any particular troubles that they wanted to bring up, we're happy to address those now. Or if any of the two groups between the two videos wanted to share any cool things that they found in the software, or have any questions of other uses, we're happy to answer those now for a little bit before we have to move on.
Nicole, I do have a question.
Yeah.
So I know one of the parts of the ethogram was for when they have interactions with other species, but in our video in group number 6, there were a lot of seals swimming around that whale. So is that a continuous point, or is that like a single space kind of thing?
Ooh, that's an excellent question, actually. I haven't actually myself worked with the sea lion interaction data. That's actually someone else in the lab's work. I imagine that would be somewhat of a continuous observation, and depending on what the whale's doing, like if it's in a foraging state, mark that as well as like the interaction, or if it's just like swimming and you see other animals nearby, that would be another thing to mark as well. And those are notes that you can make in this description section as well. So it's really like what the focus of the question you're trying to address relates to. And if Sarah or Emily have anything to add on that note as well. But yeah, it's kind of some of the observations like that are up to a bit of interpretation and in terms of the protocol that you're trying to create in terms of auditing these videos. Some of it could be subjective, and so I hope that answers your question a little bit. Sorry.
Yeah, no, that's Nicole. Yeah, that's a really good point. Yeah, especially with the Monterey feeding, sometimes they will really just be if they're interacting with those bait balls that have the sea lions, pretty much as long as the whale is going to be around the bait ball, there's going to be sea lions. So you can kind of like start them, like you can mark kind of like the start of that in terms of like when you first start seeing the sea lions, and then kind of mark the end later, but those might not be within the same video. So yeah, it is kind of tough.
Sarah, there's a question in the chat here too, or Nicole, about the hydrophone data and any abilities to incorporate hydrophone data into Boris.
Oh, that is a good question. I honestly don't know. I've only looked at hydrophone data using Raven. I know people have used like Audacity and Audition as well. But this would be a good question for Jake, because I think he's actually looked at that. But if you do find like acoustic events, you can use the timestamp that you found with those hydrophone. Basically, the way that I've done it is like within like Raven, you can find, you do some time math and you find exactly when that acoustic event happened within the deployment, like in local time, and then you can go back into Boris and like find where it would be within the video. But in terms of incorporating the hydrophone processing with the video, I don't know. I'm not sure. I know that there is like a weird selection that you can choose there with the acoustic data, but I haven't used that. I'm so sorry.
Cool. Any other general Boris questions? And like I said, we'll let these people, we'll let Nicole and Sarah and Emily take it up again tomorrow morning to talk a little bit more about some of the applications and how you use Boris a little bit more. Are there any other questions about some of the implementations or anything now? Awesome. Definitely take a chance to look at it a little bit more tonight. I know we didn't give you very much time, so this will allow us to kind of come back to it tomorrow morning and answer some more questions. So if you've never used Boris, it is pretty powerful. So take a look at that, and if you have any questions over the night, feel free to come back to it tomorrow. And Nicole and Sarah and Emily will be there to check it out and answer your guys' questions. So thanks to these guys. Huge round of applause for them as well. You know, Zoom electronic applause. I needed like a sound or something to play when people are doing these awesome presentations. So thank you guys for that. We're gonna, the Stellwagen data that these guys just showed you is actually a pretty cool transition over to Jen Tackleberry next, who will show TrackPlot. And we're almost to that spot in making our PRH files where we can throw it into TrackPlot. There's just a couple of steps after the PRH file. So we'll show you that. We did provide in that day 4 folders and in the CATS data some example TrackPlot data, so you could try to follow along with some of what Jen is going to talk about next. And it's just another way to visualize data. And then we'll show you what to do. How do we get your data there? So thank you, Sarah, Nicole, and Emily. And we'll pass it over to Jen after Will has a question.
Quick note. It looks like somebody's having issues with the day 4 folder. I just want to check it. Is anybody else having issues downloading things out of the day 4 folder or seeing everything that's in the day 4 folder on the Google Drive? Just want to see if it's a...
I had an issue that I had to sort of reload the page from the and it worked again. So I wasn't seeing things uploading, but if you reload the page again, from the link that you sent, that was what worked for me.
That's what worked. Okay.
Maybe resend the link, Will, would be great.
Okay. That I can do. Cool. Okay.
So Jen Tackleberry is worked in a lot of different places around the world, and is going to be showing a lot of her work has been in coastal Massachusetts and Maine, working with a lot of the people here. As well on some of the northwest Atlantic population of humpback whales. And so she's going to share some of that work. She's now a student, almost done with her master's degree at Moss Landing University, Moss Landing Marine Station.
Hi, everyone. Let me share my screen. Does that work for folks? Yeah.
It's coming. I don't see it yet, but it's
loading. Yeah,
it's loading.
Oh, it says it's paused. There. Is that better?
There you go. Yep.
Okay. So thanks, Will and Dave, for having me. I'm going to be talking about TrackPlot, which is just a different way to visualize this tag data. To begin with, Colin Ware created this data, and he's at University of New Hampshire. And what it is just a package to help visualize kinematic data. And if you look at the top video, that's one of their earlier programs. It's called GeoZooey. And you can see it's a really cool method to visualize where the whales are in time and space. And you can put it with, the prey data. And we also had, the focal follow boats and the tag boats. But when you look at that, it really doesn't provide too much information about what the whales are doing. It shows you where they are in the water column. And so they wanted to provide another means to better see patterns. And they came up with TrackPlot. And so it's represented by this ribbon that indicates the direction of travel, roll, pitch, and fluke strokes. So you can see in this little video at the bottom, the blue chevron is the top of the track, the gray is underneath, yellow is when the whale rolls, and then you'll see red triangles, and those are fluke strokes. And so the red ones are upstrokes, and then the down ones are downstrokes. And the height of those are the amplitude of the fluke strokes. So you can see even by this video, you can really see this pattern and how repetitive this bottom feeding behavior is. So if you're anything like me, I'm getting better at this, but this is really hard for me to visualize what a whale is doing. But you can start to see, now we sort of know what this might mean and back up at the surface, but this is sort of crazy. And so TrackPlot allows you to actually see a track and better understand. So you can see over here, you can tell here the whale's rolling on its right side, and you can see that here. And then you can see this craziness with a bunch of jerk and direction change that the whale is, doing these circles. And so this helps show you what the whale is doing, but at the same time, it doesn't necessarily explain why. And that's where cameras really are handy. And so it sort of explains that this whale is bottom feeding. You can see the bottom, the sea floor. You can see there's actually sand lance, sort of a blanket of that. And so some of that jerk is the whale interacting with the substrate, but there's also a bunch of other whales around. And so not only is this whale interacting with the environment, but it's interacting with other whales, and that can explain sort of that craziness and why it would have changed from a nice bottom side roll to sort of a different feeding behavior. And also these are juveniles. And so when you start to add in information about who those individuals are, it can sort of explain why, you know, they're still figuring out life. And so it can be a little messy. So the work I am currently doing is looking at how sex, age, and reproductive state affects the feeding methods individuals use. So if you're pregnant, you use different behaviors than when you're, you know, have a kid in tow, or if you're younger versus older, male or female. And most of this is based on using track plot and previously described behaviors from work that Colin Ware has done, Dave Wiley, Ari, all the folks at Stellwagen. And it shows you sort of like how different across here is the same whale doing lobtail feeding, but you can see how that behavior changes quite often within one deployment. And then down here are two lobtail feeding events between two different individuals, but they're very similar. And so this is pretty handy. And what I did for my work was I actually made videos of the track plot and then used Boris to audit it. So I came up with my own ethograms, and this was a really handy way to then see what the whales are doing through track plot and then export that. And with the event detectors that Sherelle was talking about earlier, they work great as well. But sometimes for these Gulf of Maine whales, they're a little special. And so it doesn't, it can lead to some confusing stuff. So here it looks like just two ascending dives. When you look at track plot, the second dive looks a little funnier. The pitch is a little steeper. And so when you start to look at the camera, you can verify, oh, sorry, it's a little loud, what this whale is doing. So that first ascent is a normal dive, but the second one is actually it feeding. And what I was looking at was what these whales, not tools they were using, but other behaviors they had to do before the lunge to be able to corral their fish. And so this is just an example of the whale was using bubble clouds, but not in that beautiful bubble netting fashion that, you know, Will showed earlier from Alaska. And these whales can do that, but this is an example of how these cameras can really help determine, you know, if this whale was blowing bubbles versus other whales with it, and in what fashion. And also shows what type of prey they're feeding on. So with track plot, this is just some publications, you know, from my circle of folks I know that have used track plot to look at animal movements and feeding ecology and how they relate to their prey, their acoustic environment, or how they use communication. And I know my lab mates are using it for other species such as sea lions and elephant seals. And so just to begin, you can, as Dave said, the information is on the folder. And so hopefully you've had access to download the program, and we've supplied some example files. You can also go to their website and download it. It's right there on the screen. And I recommend going to their site just because it is really interesting to see the different ways they visualize different types of data. And with this, you'll just need the program, and then you just need two types of documents to use track plot, and that's a VEC file and a text file. You'll also see whether you take it from the folder or download it from the website. It comes with some files that are model species. So depending on what your tagged animal is, there aren't a ton of options, but they do supply a few, you know, manatee, humpback, etc. And also they do have a user manual, which is only 12 pages, and I recommend reading it. It's super helpful. So for the VEC document, this is what we'll be using the PRH file to create, and I'm going to leave that up to Dave later to talk about this more. But with this, the important thing that we found was if you have really long deployments and you try using track plot, sometimes track plot does nothing. And so you have to actually split the VEC document into two different documents. And when you do that, just make sure you change the number of records. So that represents how much data you actually have in each file. And then for each of your VEC documents, you need a text document that goes with it. And this basically describes how you're smoothing your data out, which is already done in the VEC document. If you are using a VEC document, you can use different types depending on your data, but then the full name of the file, and this is if it's in the same file as the program. If not, then you need the entire link to that file. What model species you're using. So, if it's manatee, humpback, blue whale. The tag on time, and this is important if you are splitting up your VEC document, that this tag on time isn't necessarily the time the tag goes on, it's the time of that first line of that VEC document. And so that you'll have to change for each of your text documents that go with your corresponding VEC document. And then the name or code that you're using to ID that animal, and then end. And this is where you can also add in other data. So if your tag doesn't have GPS locations, you can have a fixed file you can add in if you're using like range and bearing from the focal follow boats, or if you have acoustic data, you can add that file in, or if you have a marker file, such as if you're doing playbacks and you want to show on your pseudo track where those playbacks occur, you can add that into this text document, because this is basically telling TrackPlot what files to pull in. So for today's example, it's a mature female. We've tagged her quite a few times during the Stillwagon Bank National Marine Sanctuary project that this data is from. And then we'll talk about it likely later, but the difference between the georeferenced and non-georeferenced tracks. And so in purple, this is the georeferenced, and that's using those GPS locations, whereas this is non-georeferenced, and so it's just based on sort of the kinematic data, not having fixed locations at the surface. So you can see they're quite different, and I was told, since I'm looking at behaviors, that it can be easier to see or determine those behaviors. If you use the non-georeferenced, it's just a little smoother versus the track line being forced into those surface fixes. So this is just going to quickly go through and show you how to start up TrackPlot and what that is. So if you open it up, this is your first screen, and you just need to copy the name of your text file and hit enter, and it'll pop up with a control panel in a window. And you can see it automatically creates 3 folders that talks about all the different dives throughout your tag deployment. And then in the control panel, you can select if you want an animal, if you want to show the flukes, make a narrow track or a grid. And then if you just grab onto the window, you can rotate it basically in every direction. At the bottom, you can jump sort of small, medium or large jumps forward or backwards. You can zoom in or out, which is the next key here. And then there's this play button, and that will automate it, so you don't have to drag it around. And while it's playing, you can change your orientation, zoom in or out. You can go faster or slower, depending if you want to really look at a behavior or if you are just tired of a section and want to skip through. And at the top, you'll see that's your entire track deployment. And so the red bar is where you're at. So you can just pull that and drag it if you want to jump to different sections. So here we're jumping to a section that looks like bottom feeding. And so then if you hit play and automate it again, you'll notice this green line above the whale, and that's actually the depth. So it's at the surface, has no bars. And then these are bars to the depth. And you can see at the bottom of the screen, it corresponds to 15. So the big bars are 10 meters each, and then the single bars are 1 meter each. And then if you want to take a photo, you can put an output, you can name it and hit save image, and it automatically does the screen grab. And then it produces 2 files, one that's a good quality file, and then one that's like a thumbnail, just in case if you're doing a lot of these and don't want to take up too much space. Then if you look at the control panel, you can hit statistics, and it has different plot options if you just want to look at the vertical velocity or frequency of pitch, things like that. Then it also has this other option to save different outputs from the track plot. So you can save point or section or a depth histogram. And in order to do that, you can put the output file you want, hit set, and then the record will light up and you can hit play. And it doesn't matter what speed you're going, you're basically just telling it from where to where you want to grab. So you hit stop and then record. And then you hit, for this one, we want to save section and then save file. And it automatically saves those files to your folder. And you just give it a minute. It has to do some thinking in case you don't see something right away. But this is the type of data that you can come out with. And that's the point data, or this is the section data. So that's that whole bottom feeding section. You can look at the depth histogram. So this is, surface feeding versus bottom feeding, percentage of time it bends it into the different depths there. So as an example, you can play with the data that we provided you. And if you want to look at, this is a lobtail feeding section versus bottom feeding section, and you can practice, exporting an image that you could use in a publication, and then export the tracks section and compare that and the depth histogram. And so if you're looking at particular behaviors, or if you're looking at whether, how much time the whale spends at the surface during the day or night or by hour, anything like that, this is just an easy way to pull out that data using a more visual program. But with that, I just want to say thanks and good luck with your projects.
Thanks, Jen. That's super super useful. That's awesome. I will note that one thing to add on to there is the example files and TrackPlot in general, I think, is PC only. Jen, do you know anything about using TrackPlot on Macs?
I do not.
Yeah.
No, I can ask Colin, but I do not know of a method.
I think everything I've heard is that it's PC only. So if you're trying to do this exercise, it's going to be PC only. But that was totally awesome. I see a lot of applause coming in for Jen, because that was really, really cool and eye-opening. And it's a really cool software. I think what we'll do, just to kind of take advantage of our time together, is we'll open up the TrackPlot exercise breakout rooms kind of at the end of the workshop in case anyone wants to stick around and do those. Other than that, they're on the website, and they're in the folder, and you can do those to exactly what Jen just said, to do those practices there in that TrackPlot folder. And you can practice opening that up and doing all those things that Jen just said, where you can watch her presentation there. And so that's super cool. And one of the things that I would add on to that is that one of the reasons in our workflow, we create TrackPlot files every time. And it's not that we're going to do a TrackPlot analysis on every file, but by doing that, then we allow for someone who wants to do, like, we're trying to give you guys lots of options to use these data in different ways. And one of the options, as Jen says, TrackPlot is very powerful to do a lot of really cool statistics and come up with it that way. So if you want to have that, and if you have all those track files already kind of made as part of your workflow, then it's easy to come in later and say, like, yeah, I want to try to learn this new analysis technique and do this TrackPlot on there. Jen, is there anything else you want to add on to that, or hints for doing the kind of using TrackPlot on their own in the exercise?
No, I think it's not too complicated once you get, playing around with it. And then that user manual is super helpful too, and it's a quick read. But yeah, I think it's pretty good.
Go ahead, Will.
No, I was just going to say there's a question in the chat if people should download TrackPlot or TrackPlot 3.
Oh, yeah, good question. I have success with 2.3. It's the version you can get off. If you're getting it off the website, I get version 2.3. If you get it from our Google Drives, it's just that version that we have in there. TrackPlot 3, I found had some issues, but maybe Jen, which one do you use?
2.3. It's more reliable, I think.
Cool.
So I think just to follow up on that really quick, if you go to the website where you download it, there's two options. One option is download TrackPlot, and one option is download TrackPlot 3. So I'm assuming that download TrackPlot is the 2.3 one.
Correct.
Okay.
Cool. Thanks. We're actually, let's talk, before we get back to our PRH file, I want to do one more option for promoting these data. Thanks again for Jen. But the idea of like creating these files, these PRH files and these .nc files, which we're going to get to just by the end of the day today, that are portable formats to be able to use in multiple analysis pieces, and to be able to do TrackPlot and be able to do other analysis with it. You can do some 3D modeling with these things. So another person who's done some cool modeling and is actually doing another workshop on another kind of 3D modeling tomorrow is Jessie. So I'll have Jessie jump on here now and talk a little bit about a workshop she's going to do tomorrow that will, tomorrow afternoon Pacific time, that you guys are all welcome to attend to as well, to kind of talk about visualizing some of these data in 3D.
Yeah, so I think Jen's talk is like a perfect transition to what I do. I'm like a freelance animator in addition to being a PhD student. So right now I'm working on an animation for Dave Wiley's group. So you were talking about the Stellwagen Bank National Marine Sanctuary data. So I'm visualizing this data and focusing a little bit more on the aesthetics, but using the same type of data that we're getting from the PRH files and creating these like visually aesthetic animations. So tomorrow at 2 p.m., I'll be giving a workshop on how to bring your PRH files into a 3D animation software called Autodesk Maya, and sort of showing you how you can make these kinds of beautiful animations to go along with the data that you've worked so hard to curate. So a lot of that is just taken straight from the PRH file. You get a GOP track, which will tell you the position in 3 dimensions, and then you also get the rotation, patrol, and heading. And you can just use those to start your animation, and then you can add your stroke rate or whatever you want on top of that. So if you're interested, I'll have Dave send out some information about that workshop. Thanks.
Sweet, and Jesse, if you can put some of those links in the chat, that would be helpful. And then I also have made, I will share this screen right now. I've also in the day 5 folder document. So in our workshop materials in day 5, I put this text file in here that has all of the links to Jesse's workshop. If you want to check that out tomorrow afternoon as well. So Will and I can send that out later on, but also these are the direct links in that text file in the day 5 workshop as well. So you can see those, and I think Jesse will put some of those in the chat as well. Jesse, will your workshop be recorded at all for awkward times for people?
Yeah, and it'll be uploaded as one of the links that I'll send out, and I'll explain all that.
Sweet, that's awesome. So thanks. There's just really a lot of cool things you can do with this data. So a lot of everything we've just seen of the last few workshop for presentations there have relied on either the video synchronized with the data or the GOP track. And so we're gonna spend the rest of the day today finishing those up. So take about 2 minutes and see if you can get your workshop back up to space here, so that you have find where you were in your MATLAB PRH tool, where we just saved this MATLAB file in step 12. And we'll come back to that spot here. We're going to start with section 13 here in about 2 minutes. So get caught up there, get all your ducks in a row here, and we'll start here again in 2 minutes. Meanwhile, I see a couple other questions coming in that we'll take a look at here. Or not? No, that's good. Okay. Yeah, and a couple other folks said, yeah. Carrie said that, yeah, the trackbot is almost definitely PC. Just to remind us where we were, we have now, after running step 12, we have created a PRH file, which is available in the cat. If you were unable to create that file, the 15 or 20 of you guys who were not able to create that file, that is now available in the workshop example data. So you can download that. You can see it's a lot smaller than our raw data even, because we've now decimated all of our data to 10 hertz. And it just kind of has the main important files in here. So this is a pretty portable file. We'll talk about a couple more portable files here as well in a second. So this is our main file. And from here on out, we're basically just making adjustments to this PRH file. So we're adding in a couple more variables into this PRH file. And just if you guys are using MATLAB, one of the things you can add in, just to kind of the switches as you're looking for data. I'm looking for an example here. I'll go up to find them. But when you're saving data directly into a file, like if you're saving this PRH file, so this is the first time it's saved. So you're saving all these data into your PRH file, all these different variable names directly into your PRH file. Then the next one here says like, okay, I'm going to append on, I don't want to overwrite this file. So I'm going to append on these two variables into the file name. So using this append switch can be really useful. So that's kind of what's used integratively into these next few steps, to have your PRH file and to add in a couple more variables after that, or to fix one of the variables in there. So you save your file name and then you append on a new variable in there. Well, I see a lot of questions coming in, but I'm not reading them. Are we all good?
Yeah, so there's a few little errors here and there. Somebody was getting an error in step 10A that it wasn't finding the function or variable last doer.
Yeah, that was, I think we fixed that one. That was a duration error that was coming up because it was trying to read extra files. So if you upload your GitHub, that should fix that one.
Okay.
She said she fixed the GitHub repo this morning. That could be a file path error where you're using an old version of that file. That someone had that error yesterday. So we can go over that with you this afternoon. If you're having problems with that specific error, it might be an update file error, and you can check that you're drawing your file from the right path in MATLAB. So I know there's a lot of versions floating around, so that has been a common error.
And then there was one other from somebody who might join us this afternoon. Was having a little trouble in part 8.2 back a little ways. Unrecognized function or variable MT.
Okay. Yeah, that's we'll have to come back. We'll have to come back to that, I think.
Sounds good.
Not sure what that is now.
That's what we got so far. Cool.
Okay. Let's take the last 20 minutes today to kind of go over a couple of examples here. We're now at this position where we're adding GPS data into the file, and there's a couple ways to do that. So we'll show you an example that I've written. My GPS it's trying to be very cat specific, and it's not the prettiest stuff in the world right now. I know there's way better ways to plot GPS data than what we're showing you. But this is just for this cat specific file for these versions. The GPS data from the file there's a bunch of different ways to convert GPS, and CATS even uses a bunch of different ways from it. One of the things it uses is this UBX converter from the raw data that comes off the file, and you download ephemeroides data, and then after your deployment, and then it finds where the satellites are. It uses a fast lock essentially technology. But you might also have a fast lock on your tag, or you might have other GPS positions, or you might have GPS positions just from using binoculars on your boat to have GPS positions. So there's a bunch of different ways to import GPS data on your tag. This will be just this one cat specific one. It's a function written here called add GPS from the POS file. That's this POS file that's in your example data folder. So we're going to read from that file, and it's just kind of a funny format file. So it's really kind of cat specific, but we'll have this function here to run. And then after that, there's this next script down, the next cell down here, we'll have another version as well should be more flexible for other things here. Oh, sorry, I fixed this earlier. So I have to add in here, I'm telling it where this map file location is, and then I'm telling it to clear it right away. So I can't do that. So run this file function. Sorry, I tried this just earlier today. My bad. Okay. Well, we will maybe skip this step for now, as I worry about that. So basically it imports the POS file, but that's not working. Let me switch my screens here, and I'll show you another version that does work, just so you can see it, and we'll troubleshoot errors later on. I'm sorry, I practiced this a couple of times. Stop this share. We'll share this one from here, just so you can kind of see what it could look like if you get it to work. And then the next ones should work as well. Okay. So, just because I want you to see what a final GPS position and stuff looks like. So let me share this screen. Okay. So this is a MATLAB 2020 version. Should be able to run this file here. And it's busy here. So it's basically trying to import that POS file into my data file. So you can see it creating a couple of variables here on the bottom. And hopefully other people are able to run this. I don't know why it's given that error in that other version. So it's basically looking for bad data points. It's trying to remove any bad data points that are from that POS file that are offset. And it's looking for anything in the POS file, like some errors that we've had in the past is that the POS file, the GPS data is offset from the tag time. So it's like finding, okay, is there any tag offset times in there that are inappropriate? It's going to pop up here a couple of plots here in a second. So right now what it's doing basically is it's updating this PRH file and the truncate file with new columns that have the GPS data integrated in there from the POS file. So if you have POS file data in your tag, that's what this is doing and integrating those pieces in there. If you don't have that data, then that's what the next step will be for down here, but it's still kind of integrating those pieces. And then it's going to resave those files, which is what takes a while to run this one, and longer when you're running Zoom and things like that. But it'll resave these files. As you can see, this file getting bigger, and it's just been created right now. It basically rewrote that PRH file with a new data column in here, this GPS data column, which now has all of the GPS data. Essentially, I'll open this up after it's finished plotting here, but essentially it has all of the GPS. Basically, it's going to be nans everywhere except where you have nans, meaning not a number. It's basically the MATLAB code for not having existing. It'll have nans everywhere except for where the GPS actually exists. So like surface scenes from your animal, where you actually have a fast lock position happen up. Or if you use Argos, you could put in an Argos position in those places. And so it's going to be this changing. GPS until now has been this file with just your kind of general location. And now it's going to have basically like time referenced GPS locations in this file to use that for. So we're still waiting for it to kind of pull up this plot right now. And the second function in here is the plot map from POS file. And it's just basically, it's another way to just a quick plot of your data. And it's taken a while because it's trying to import basically shoreline data and things from wherever your location is. This data is from the Antarctic, so it's actually not going to have any good data from there. But it's just a quick plot of your data to kind of check what's imported. Here it's popping up, and it's basically a plot of the data. And you can see that in the CATS versions, we have a number of points in here, and some of them are better than others. So the track of the animal is actually kind of embedded in here. If I zoom in here, you can kind of see better this track of the animal. You can kind of see, oh, okay, this is the tag on the boat, kind of collecting data. These are different surface scenes of that animal as it's collecting data. Then these individual outside points are kind of bad data points, and it's still integrated. And you can see that actually in one of the plots that it makes here is this plot. One of the other plot that sticks out is this is a plot of where the GPS location corresponds on your time depth profile. And when the GPS plots are at the surface, those are probably going to be pretty accurate data points. Where you're getting GPS points that are not associated with the surface, those are probably inaccurate. And I'm not sure why the GPS hardware creates those sometimes, but it is a thing that you come out. So one of the steps we'll do is filter out those bad data points in this next step here. I see a couple of errors popping in, and we'll try to troubleshoot those individually. Those are, some of those name-based files will be you should be able to just write in a little bit different format. That means your PH file isn't loaded correctly. Just want to kind of run through these though, so you can kind of see these processes in a few more minutes here, and we'll have it on the record, and then we can troubleshoot later on today as well. So I'm going to run this next step here. This next step is now importing what it is. It's importing this is where you can import your own data here. So I'm going to go back to this file here. What it's creating is this GPS, this chance to actually import your own GPS data. So this own GPS data here is your lat long, and you can come from a lot of different locations. So I usually put in, at least in our files, I put in the tag on location, which I know is a known point. I also put on, this is the first file position of the Argos after the tag pops off. So it's a pretty good indication of the location of where the tag comes off. Even if you have no other, GPS points, having a tag on and a tag off location can do a lot to sync up your track to get it geo-referenced in your pseudo track. So you can do a lot with that, just those 2 points. But if you have another set of GPS points from a different fast lock, or if you have manual positions from focal follows or something, you can put all those into this place as well. And then this next step is going to sync up those points with your data. I see some questions. If you're trying to actually make the plot, some of these plot functions, I couldn't put them all on GitHub because there was an error in GitHub. GitHub can only take a certain size of file. So some of these map files are actually in a different place. They're in the Google Drive. They're in the Google Drive, and there's map files for day 4. You should be able to find those files. I have to ask you to locate those files. Any files should be in here if you can't find those pieces. That's not quite the GE point function that Arena was asking about, but one error might pop up is looking for those map files. Okay, so just to kind of show you what's going to happen here. So you find this up, then you have this new, when in section 13B there with the GPS hits file, it's opening up that GPS hits file, and it's adding in those 2 points that I just said, these first 2 GPS hits, the tag on location and that first Argos hit. Now, like I said, I'm going to use that Argos hit actually for this data as a kind of a tag off location. It's our best guess for the tag on. Even though that hit is like several minutes after the tag popped off, it's going to be pretty close to where that final file is. And if I decide later on that actually it might have drifted a while, I can delete it later. But for now, I want to use that as my final hit. So what I can do is I can zoom in here on this file and press enter to adjust that point. And I'm just going to adjust that. I'm going to adjust that point to be closer to where my tag actually came off the whale. So I kind of use that. I'm telling it right now to use that final Argos hit, that first Argos hit, as a point on my whale. So I press M to move that point. I'm going to be over here by my point, press M, and then click over here closer to where the tag is actually still on the whale to say like, that's where the final tag location is going to be, is that very first Argos hit, that very first high quality Argos hit. So we'll have that data point. So I have my tag on location over there. So this part looks good. I don't have a lot of other manual hits. I imported just those 2. I'm going to say okay for that. I'm going to press enter to accept these points. And again, a lot of these things are pretty clunky user interfaces, I understand. So feel free to use your own. All we're doing right now is trying to integrate the GPS into your data. So if you have a better way to do that, you can definitely do that. And you can use the rest of the tools by integrating in different ways. So I'm pressing Q to move on to this next section. And now we're going to try to identify these bad data points in here. So again, we can zoom in or zoom out to identify this. Right now it's identified in green here, a lot of these points that imply that the whale was going more than 6 meters per second. Like it's very, very fast between points. It's kind of highlighted those points and saying like, those are probably not right. Those are, the whale would have to be basically jumping in space to get those points. So I don't have to zoom in here. So I can press enter, and then it gives me these options here to either click on an individual point to delete it. I can just delete that point by clicking on that point, and now that point is no longer part of my data set. Or to delete all of the green points, I can just press delete, and that's going to delete all of my green points there. Now I want to change my zoom. I want to zoom in a little bit. So I'm going to press enter to zoom back into this spot here. And you can kind of see both like all of the points and these kind of tracks. And you can kind of see that some of these points are well adjusted in here, but some of them kind of imply that the whale like jumped from here to here to here to here. So those are the ones I'm going to try to like clean up a little bit. And this is just like a cleanup tool because GPS points can be a little bit messy as it's trying to be accurate. And there's other ways to filter this data. Some people use Kalman filters or other more sophisticated ways to do that. And so, you're welcome to do those kinds of things. This is a way for me to kind of like picture and have a better sense of what my data is, and partly because sometimes we don't get very many hits with our GPS locations on these animals because fast lock can be problematic. There's a question about what are the axis locations here. These are meters off of a certain point. These are UTM coordinates, and so they're not great locations right now, but we'll get to better GPS locations for now. For now, this is just mostly a visualization tool. But I can keep now going in here. So I have my zoom set correctly. So I'm going to press enter. And I'm just going to start cleaning up some of these points in here. Clean that point up, clean this point up that kind of is off here. If I think this is my tag on location, I'm going to go ahead and set that as my tag on location, just get rid of these points. I have enough points here that it's okay to delete some of these other points because, mostly I just want to, I have enough points here that I just want to be accurate more than anything else. More than anything else, I just want to be accurate and be able to have the best points I can. I'm going to press enter to then see this, delete this one. I'm going to press enter to go back and zoom in a little bit. I'm going to zoom in on this section. Just cleaning up a lot of my points here. Press enter so I can clean up these ones that are kind of off kilter here. And we're going to make the pseudo track here later. So basically anything that is just one point, I'm going to assume is unlikely to be accurate. Anything that's off by itself. I'm looking for places. I really trust the ones that have like a lot of GPS points all kind of together, clustered together. Those are going to be more accurate because like you're getting 10 GPS hits a second. If you only get one of those points and it's all off by itself, it's probably not going to be the most accurate thing in the world to use. But if you have a cluster of points all kind of sampled in the same second, you're going to be better off. I'm going to press enter one more time so I can change my zoom here. I'm going to really zoom in tightly. It looked like there was a cluster of kind of points in here that are all kind of off. So I'm just going to clean these ones up as well. So I'm going to clean up this one and these ones that are kind of off by themselves. Because again, like we're collecting GPS data at 10 hertz. So anything that's kind of that's off by itself, I'm going to assume is not as accurate as anything that's collected with a lot of locations within 1 second. Okay, we're getting pretty good here, and you can see the kind of that track between them. So we'll go back, kind of look one more time. We'll get rid of these points down here. Zoom back out here. Okay, so select that one section. I'm going to delete this one, and this one, and this one. And now we're looking pretty darn good. So now we have a pretty good track in here. Maybe get rid of this one more over there too. And we can see that there's a lot of good points in there. And then we're keeping my number 2 here, my Argos hit, all at the end here. These 2 lines are connected, but that's just because it's those 2 points, one at the beginning of the track and one at the end of the track. So this is my manual hits that I entered in that GPS hits points, manual hits from that GPS hits sheet, and all of these are points directly from the tag. So I'll go on from there. I'm just basically going to press enter, and then I'm going to press Q to finish this and kind of synchronize this up. And I'll show you this last step of like making these last few files here so that you have these nice hits together. So here's my plot now. Now, when you make this is all set up in one cell here. So this gives you the chance to kind of look at your data and say like, oh, you know what? There are still some bad points in there. Or, oh, that looks pretty good. And so this is my plot from my blue one is the pseudo track, just basically saying, okay, start here and just integrate the inertial sensors to go through there. And this is from a function called ptrack that is used in the animal tag tools that Stacy talked about earlier today, and just basically integrates your depth and your heading and your pitch and just integrates that and your speed and integrates those things and says, okay, if I just assume that those are all perfectly accurate, where does the whale end up? And it kind of integrates those points. Now at the end, especially, notice kind of at the end where the tag starts to slip, you start to get a little bit off. And because you're integrating error, any small error over time will add up quickly. So having these GPS points can really help you make a more accurate track, because it can integrate your error and distribute your error between these points. And you can see that once you do that, you end up getting what we think is pretty accurate. And the track kind of like matches the GPS points pretty well. And that's going to be our best guess of like kind of the 3D orientation and position of that animal over time. So creating that GPS track is a critical thing here to be able to then do things like, so now once I like that position, once I've done that file successfully, and if you don't like it, you can run it again. I kind of spits out where the end of the track is, which if you didn't have a final position, that would be a useful piece of information for you to know. And you can compare that to where you picked up the tag or whatever. Then the last thing to do is to kind of start saving these files, and then it's going to both save these figures so you can have them as part of my quick look that I make at the end, which I've showed you guys earlier, and I'll show you guys here in a second what that quick look is. But it also then makes a couple other files. So let's run this cell. And what it's going to make is it's going to spit out in my folder here a quick look. It's going to save these files into the quick look here. So it's going to like save that ptrack file there. So you have that as a record for later on. It's also spitting out this it's just can't move that file around, but I'll show you what else it's making here. It's making this ACQ file, which is just a text file with all the PRH data in there. So that's useful to locate into, it was a program called Acknowledge ACQ that you could load right into that program. That's a visualization tool, much like TrackPlot, to help visualize your data. It's also spitting out this GeoPtrack KML file, which for a lot of people, that'll be the most exciting part that comes out of your data, right? Is this geo-referenced track on the planet that you can make into the KML file, and then you can really helps you visualize your data. So one of the things we'll do for our quick look file is basically take screenshots of this data of where my whale is on the planet, and you can put that in with your shoreline data, or you can integrate that with a lot of other graphing and mapping softwares to be able to make your kind of track of the data. So one of the things that I do with these right away is to make basically a screenshot of both like the kind of the track of the data, and I'll save that file in my new PRH folder. In my quick look file, I'll just save a file called map. So I'll just put my whale name in there, 20031258. I'll call that KML. And then I'll put in a kind of a bigger view. So I like to kind of like put my kind of give context to where my whale is on the globe. So I'll make another screenshot here. Mess with the zoom window. another screenshot here with just kind of the general location of the data. So I can say like, okay, a whale was tagged in Charlotte Bay, and I can kind of see that condition of that. So when I look through my quick look later, I can kind of really see very easily where my data is, where my whale was. Okay. Finally, and that's just looking for, this is just looking for us trying to move the files around. Finally, what it should also create are two other files here. One is this trackbot file. So I wasn't able to copy this file where it had that error that spit up, because I have it set up to try to, like, whenever in my file structure, and I'm not using the right file structure here right now because I switched computers, but usually it's set up in my example data to always make a copy of my PRH file in just a general PRH file in my tag data folder, so that you can have a kind of all of my PRH files all together, not necessarily in separate folders with the whale with all the other data and the videos. I like to have a separate copy of my PRH file, so that's where that error cropped up, and I just have that copy file in there. You might have to comment out that folder if that's giving you errors in the way that you're structuring your data. But then it does make this this trackplot file. And the trackplot file is exactly what Jen was just talking about. So basically integrates your heading and your pitch and your roll and that pseudo track, either the raw pseudo track or the georeference pseudo track, and makes both of those files, and makes this trackplot file that's going to spit out here. So you have both this trackplot file and this georeference trackplot file for every one of your PRH files to use. And all these tools, again, even if you got an error on one thing or another, you can use these individual tools to help craft your data and make it into a certain way. That's basically what I wanted to show you today. Oh, the last piece too, this is a critical thing, and this is what James is going to talk about tomorrow, is this idea of an NC file. So I'm going to run this last little bit here too as well, which creates something called an NC file. And an NC file is, I need to find my tag guide here for this, which is in my our workshop folder. So I'm going to navigate to my workshop folder. And in my workshop folder, in my example data, in the CATS folder, there's this tag guide. So I'm going to import that CATS tag guide. It's going to take some information out of there, and it's going to spit out what's in the end. It's just basically reading all the same information from the PRH file and all that kind of metadata from the tag guide. This is a file that James wrote to be able to do this function. It's going to give you a plot of your data, and what it's creating is this structure called an NC file. And an NC file is one of the, it's basically a portable file structure like a PRH file that is more readable than things like R or Python or other tools. So it can be a really useful format to have as part of your structure, to be able to, as part of your workflow, to make these NC files, because then they can be really easily imported into and be used with things like the tag tools, the animal tags tools. James has reminded me that Danuta wrote a lot of these files, this NC creation actually, and who is also here today, and James edited these to make it work for our data sets. So there's just a cool opportunity to use these .nc files. So I know there's, I even had some errors cropping up there in my file, so we'll go back and figure out what is happening there. But if you were able to work on these map files, that's awesome. If not, those individual tools might still be really useful for you as you get to your data set. So I'd remind, basically what I end with today is the idea that, like, getting to this PRH file is pretty solid. And then if you can get to there, we should have a prize for the first person who can get to that, that PRH file, that final PRH file, and create that PRH file. And then you can do these other add GPS things to them and whatnot. But if you can get to that final PRH file with your own data, we should have a prize for that, and we can help you then add GPS in or create the video files from that. We're kind of out of time for the day, so we'll save the last two steps, this making a quick look file, which are these nice quick look file formats that we like to make with our data. And again, this is just totally optional. This is just like a file structure that we have in there that can be really useful for people. But it's just a way to kind of quickly look when you start getting a lot of data, to be able to remind yourself, like, oh yeah, what was this deployment about, or what was that deployment about? So it just gives you a chance to kind of have that quick structure of like, let me put in a picture of that video, a picture of that whale, of that animal, some screenshots from the video, the drone shot if I have it, and then integrate those pseudo tracks all into one place. So you can kind of see all those things together. This is the whale we've been working on in that track that we just made there. So you can kind of see all those things in one place. And then we'll also start tomorrow with a brief overview of then that last step, which is this vids data wireless step, to actually sync up the video and the data. For that, if you come in the morning with a ability to hook up your computer to a monitor that has high resolution, so bigger than 2,500 pixels, that will be the easiest way to do this. Although you can do it as well with small resolution monitors, but you need multiple monitors in order to be able to do this step. So we usually set up a whole workstation with one place. But that's basically as far as we'll get to today. I know there's some errors cropping up, so hopefully we'll be able to address some of those for those of you guys who can be there in the afternoon session. I'm sorry, it didn't go super smoothly, but that's where we're kind of at for the day, and we'll figure out where those things are coming from.
And for the wiki, you know, as we've sort of made some updates to the code, you know, even over the course of this week, some things in the wiki might be a little out of date now. So run through, and if it asks you for something that you know we told you it didn't need to ask for, or vice versa, or something like that, or the graph that pops up looks a little bit different, please let me know. And my goal is to sort of update it so it's up to date on the most recent code changes.
And I think I think the wiki is actually not updated past the making the PRH files. So those GPS points and the map files and the making the video files, we're still working on that aspect of it, partially because I'm still updating the code at all times. So we'll come back to that, and that will be an updated part of it. But if you're looking for that online right now, it does not yet exist. Cool. Yeah, we'll wrap it up there for today. We'll come back in an hour for anyone who wants to try to troubleshoot some of these steps with us, and show us what you guys got, and ask other questions, and we'll be available for that. So thanks everyone for another good day. Hopefully that was really useful. We'll end tomorrow with some more information, some troubleshooting, finishing up that last video processing steps. And then we'll ask for some feedback from you guys. So thank you so much for your participation.
Awesome, good stuff.
Yeah. Cool. Well, I'm going to stop this, Will, so we can start the recording, and we can check in a little bit.
Sounds good.
Right on.